Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math basic course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on aside as we jump into section 2.5 in the Big Ideas Math Integrated Math 3 textbook on transforming quadratic functions. Now, I'm personally a little excited about this section because this is the first time I believe that the Big Ideas Math textbook set entrusts us to graph quadratic functions without use of a table. I did a quick scan of the lecture portion to see, wait, where are their tables? And there aren't any. I do believe that they're saying use the parent function to do transformations. Now, what's also nice is I hope this lecture portion can go kind of briskly. I don't know how long the problem set will go. I think it's 49 problems, so might be a while with a bunch of graphs, but I hope we all figure this one out together and do it well and use this going forward into hopefully when we do cubic functions and square root functions and cube roots and rationals and logarithmic and exponential and sine and cosine tangent and all these different kinds of functions that we can use the transformations off the parent function to do so. Vertical stretches and compressions, horizontal stretches and compressions, and I'll show you how to make them also vertical when you kind of need to. Translations, and I'll start with translations as we plot the vertex and go from there. 1, 1, 2, 4, 3, 9 style. I hope you know what I mean when I do that. If this is your first rodeo with me, you might not know what it means, but think about what happens when you square these numbers. 1 and negative 1 squared, 2 and negative 2 squared. Anyway, I might be jumping the gun a little bit, but the book's not using tables, which I'm excited about. Anyway, I'm going to attach graph paper for you, the same kind I'm going to use. I may be using the taller graph paper. It doesn't have numbers on the scaling, but I want to do those with quadratics so we can hit more points and really practice that. So jump to the description section down below to find the PDFs of not only the problem set with the lecture and such, but also the graph paper if you'd like to print any of that out and follow along, and find the timestamps according to what you're trying to find. I'm going to start with the lecture, then go to the problem set. Without further ado, let's go ahead and get started. We're going to go to section 2.5, and we're going to learn to describe transformations of quadratic functions and write transformations of quadratic functions. It's really no different than anything else we transform, only I think here they really get to hit vertex form. Boom, right here. I'm already just going to point it out right now, and this is the name vertex form. A times x minus h quantity squared plus k. That is the form that we're going to be basing things off of, and I'll let them explain it for you, and if they don't in time, I'll be doing it as well. Quadratic function, parabola is the U-shape, vertex of a parabola is where we hit that bottom point, and then vertex form is what you're looking at boxed. Okay, describing transformations of quadratic functions. No different from what we've been seeing. A quadratic function is a function that can be written in this form. This is known again as vertex form. I'll just write VF. Vertex form where a cannot equal 0. If a was 0, x wipes out, the squared wipes out, it's no longer quadratic, it's just a constant. A has to be some non-zero value. The U-shaped graph of quadratic functions called a parabola. In section 2.1, we graphed quadratic functions using tables. I didn't. You can also graph quadratic functions by applying transformations to the graph of the parent function, f of x equals x squared. They're going to let us do it without a table. Look at that. They're saying table, nable. No. Okay. Now, we're going to break down how this vertex form truly works out. It's not just the vertex form. It's how these things transform your graph. And then, therefore, why it's called vertex form. So there are horizontal translations which exist inside of the function itself. The x that's being squared may not just be x. It may be something else within that x, such as x minus h. Now, I've brought this up a lot before, but look at what they're doing here. If f of x is x squared, then f of x minus h is x minus h quantity squared. This takes place of x right there as an input. We saw that in, I think, section 2.2. Might have been 2.1 or might have been 2.2. I think it was 2.2. Anyway, it just takes place of your input, but the x minus h means if h is greater than 0, it'll truly show up as a minus, and we're going to be shifting to the right. And if h is less than 0, it'll look like a plus. It'll look like x plus 2 or something like that, and we're going to go to the left. And the whole reason being, again, we're not using a table, so we're going to have to trust this, but the whole reason being is if it says x minus 2, that means our x's need to be 2 larger than they were before because they're about to be countered by something subtracted by 2. So that's why you have to go 2 to the right, because your inputs need to be 2 greater than they were. And if it says like x plus 2 to go to the left, now our x's need to be 2 smaller because they're about to be 2 added to them. That's why our inputs need to be 2 less than. So when there's a minus in there, you do the opposite, you go to the right. When there's a plus in there, you do the opposite, you go to the left. Anyway, vertical translations are outside of the function. You take the function and add k. K can be greater than or less than 0. K can be 0. But you follow the sign. If it's a positive number, we shift upward. If it's a negative number, we shift downward. So x squared plus 2, x squared minus 2, things like that. Shift up and down. And those both exist in your vertex form equation right here, and I know I'm probably jumping the gun and talking about it, but they call it vertex form because we can place our vertex at that hk. We can translate h units left to right, k units up and down, plot the vertex there, and graph off of that with our transformation. Okay, examples of these translations here. I kind of mentioned some out loud, but let's describe the transformation of this represented by x plus 4 quantity squared minus 1, then graph the function. X plus 4 quantity squared means we're going to translate 4 units to the left. You can see the x minus h in the formula, so we're subtracting a negative 4, right? That means we're going to be going 4 to the left, right? And listen, that's another way to describe it, right? The formula has a minus, so how do you turn it into a plus? You're subtracting a negative, right? H is negative 4, but the reason is because what I stated before. Plus k, it's minus 1, so we're adding a negative 1, therefore k is negative 1. So we're shifting 4 units left, 1 unit down. That's what they're stating. Translate 4 units left, 1 unit down. And what they do is they take the parent function and translate there. So you're going to have to know how this parent function works. So let's break it down one more time together, especially if you haven't done it with me. 0 squared is 0. 1, 1, 2, 4, 3, 9. You can't see it up here, but that's the plot. Reflect the pieces over, axis of symmetry. Negative 1 squared is positive 1. Negative 2 squared is positive 4. Negative 3 squared is positive 9. 1, 1, 2, 4, 3, 9. Take those points, graph it, and you can also shift. What you'll tend to see me do on the graphs, I know I'm going to have the parent function there if they request it, but I'm going to plot my vertex. 4 left, 1 down, negative 4, negative 1. Then from here, I'm going to go 1, 1, and reflect. 2, 4, and reflect. 3, 9, right here, 3, 9, and reflect. My guess is there's another section coming up. Let me find its name. Section 2.6 is on characteristics of quadratic functions. I'm sure they're going to mention the axis of symmetry. I'm not really going to talk about it right here, right? But this guy right here, it's an easy way to show that reflection, but I'm going to save it for when they talk about it, probably in section 2.6. Anyway, that's how I'm going to end up doing the graphs. I'm going to go based off my parent function. Hopefully you're okay with that. 1, 1, 2, 4, 3, 9. Keep that in mind. 416, 525. All right, let's get to reflections in the x-axis, or reflections in general. If you reflect in the x-axis, you're flipping the graph over because you're changing all the y values. That means you're making the f of x negative. Making the f of x negative. That means make x squared negative. Now, if we use a table, we follow our order of operations. We square our value, then we make it negative. That's why all the signs turn negative. So it's still a 1, 1, 2, 4, 3, 9. It's just it's downward now instead of upward. Reflection in the y-axis is quite interesting because the original graph and the reflected graph are both the same thing. These parabolas are symmetrical, so flipping it over this way is not changing the graph at all. 1 squared is 1 and negative 1 squared is 1. They both have the same height and the same distance away from the axis of symmetry. So y equals x squared is its own reflection in the y-axis, whereas this one flips over. Now, it depends. If you shift this thing over first and then they say reflect it over, then suddenly it's going to flip over, to this other side like this, boom, right there, and then it's over there. But it depends on how you do it. They're probably going to have you reflect first, translate second. Who knows? I don't actually know. But this is what makes it what's called an even function. Squaring a negative turns it positive, whereas squaring a number and then making it negative keeps it negative. There's the difference. I'm going to talk about vertical first. There are vertical stretches and shrinks, not unlike what we talked about before. When you multiply some a by your y value on the outside, if a is more than 1, it'll stretch. A stretch also looks like it becomes narrower because we're pulling it up more for those same x's. So instead of going over 1 up 1, you might go over 1 up 2 if you're doubling it. And instead of 2, 4, you go 2, 8 because you double the 4, things like that. So you vertically stretch it, taller y values for those same x values. Vertical compression or a vertical shrink is when you're multiplying by a value between 0 and 1, assuming it's a positive number right now, between 0 and 1, like 1/2, like 2/3, 1/5, things like that. And then in those cases, it's a vertical compression. It looks wider because the values are closer to the x-axis because you're taking half of your heights or a quarter of your heights or whatever they are. And then they get that shrinkage going. So what you see in red is an example of a vertical compression. Vertical compression. Now, horizontal stretches and shrinks, we talked about this in section 2 too. It's a little backwards thinking, just like the x minus h. Minus means you go to the right, plus means you go to the left. Well, same thing here. You multiply by a value inside, and I'm more keen calling it the letter b, because I like a kind of being on the outside, but I guess they call it an a, so whatever. If a is a number more than 1, like 2 or 4 or something like that, it's not a horizontal stretch, it's actually a horizontal shrink, because it's inside the function. Your x's, if a was 2, and we're going to see a 2 later, I'm sure. If a was 2, your x's now have to be half the size they were to counter the fact they're about to get doubled. So when the x's are half the size, those are your inputs. They become that. So that's why there's a shrink. It's a shrink by a factor of 1/2. So as a gets bigger, your graph compresses more horizontally, which means it stretches more vertically. And I'll show you how a horizontal stretch or shrink can turn into a vertical stretch or shrink as a result of something. Or a horizontal stretch can turn into a vertical shrink, and a horizontal shrink can turn into a vertical stretch. Anyway, so there's a backwards effect. Make sure you keep that in mind. Let's take a look at the examples. And remember, I'm not big on the horizontal stuff, really. There aren't too many graphs, too many functions that you need to be forced to use them. I'll talk about them, but I'm also probably going to transform them into verticals whenever I feel it's right. All right. Describe the transformation of f of x equals x squared represented by g. Then graph each function. So here's the parent function, and this example, part A, is negative 1/2 x squared. Two things are happening. The negative means we're reflecting over the x-axis. We're making the y values and making them negative. And the 1/2 in front of the x squared means we're vertically compressing this graph by a factor of 1/2. So we're shrinking it, flipping it over and shrinking it. And that's where they say those two things. Vertical shrink by a factor of 1/2. Here's where they name the factor. And they also name reflection in the x-axis. Flipped over. And you may say it looks wider. It's not really that it's wider. Remember, instead of 1, 1, it's 1, 1/2. Instead of 2, 4, it's 2, 2. You take half of 1. You take half of 4. Things like that. That's where we get those points. G of x equals 2x quantity squared plus 1. Let's talk about the plus 1 first as far as how I'm generally going to do the graphs. I know there's a vertical stretch. Excuse me. I know there's a horizontal compression on this one, or horizontal shrink as they'll call it. But if it comes to me graphing, I'm really going to talk about the translations first and graph everything in relation to it. So my vertex is at 0, 1, because we translate 1 unit up. That's what they're talking about, translation 1 unit up. Always describe it last, but if you're going to graph it, maybe graph it first with me. But notice the 2 is inside the function. That means that's part of the horizontal components of it. Because 2 is more than 1, because it's a bigger number, that actually resembles a horizontal compression. Instead, x's need to be half the size they are. So you're going to horizontally shrink by a factor of 1/2. Horizontal shrink by a factor of 1/2. That means instead of going over 1 to go up 1 and over 2 to go up 4, you got to go over half those amounts. Over 1/2 to go up 1, over 1, that's half of 2, to go up 4, and things like that. So you're shrinking horizontally. Your inputs are becoming half of what they are to go up the same y values as you would have before. Now, here's what I'm going to do a lot of with these. Notice 2x squared is 2 times x quantity squared as well. That means you can square the 2 and square the x. So I can also rewrite this as 4x squared plus 1. Now, what did I just do here? I just turned what was a 2 inside the function to what is a 4 outside of the function. 4 ain't being squared no more. 4 was already squared. The x is being squared here, and this is the same graph as that, but now this thing is looked at more as a vertical stretch by a factor of 4. So, does this still work? If I go over 1, instead of going up 1, now I'm going to go over 1 up 4. Yes, it still works. So, I can turn horizontal compressions into vertical stretches by squaring, I want to call it a b value, by squaring the value, the parameter that's inside the function. You can turn horizontal compressions and stretches into vertical stretches and compressions respectively, especially if you feel, oh, they actually just, they mentioned this. I didn't notice that. In example 2b, notice that g of x equals 4x squared plus 1. So you can also describe, I didn't even notice they said that. I'm very sorry. And this is what I'm going to do a lot of, and I'm actually glad that the book says it because that gives me more leeway into doing it as often as I can. Generally, we don't like to do horizontal things if we don't have to, and if we can deal with it, we will. All right, let me take a sip as we figure out what's happening next. I've already said a lot. And remember, I don't read this stuff beforehand. I did skim to see that they didn't do tables, and so far no tables, which is awesome. Writing transformations of quadratic functions. The lowest point on the parabola that opens up or the highest point on the parabola that opens down is the vertex, where it bottoms out or where it tops out, okay? The vertex form of a quadratic function is this. Notice that there is, I'll talk about it. A, h, and k are involved. A can't equal 0, and the vertex is at hk. So this is where we can do those graphs in that way, like I stated. You can relate everything. You can translate your vertex first and put everything in relation to that vertex. That means the translation already occurred. You don't have to worry about the translation after that. Just worry about reflections and stretch factors. From there, you can plot from the vertex and just kind of call it your new origin. Over 1, up 1, over 2, up 4, things like that. Don't worry about what the actual x and y values are. Just worry about what the points are with it. All right, A is a reflection. If it's negative or positive, it's not a reflection. And then it's a vertical stretch or shrink. HK is the, sorry, I just saw a text. HK is the vertex. It's also the translation, right? Horizontal and vertical, but that's where we plot our vertex. Okay, notice, here's what I was going to mention. Notice there's nothing in front of x. If suddenly, and I'm going to make up an equation, 2 times 3x minus 6 quantity squared plus 1. Notice if there was a 3 there, this isn't in vertex form. Not truly anyway. There's something you can do with it, but even I would want to do at least one more step to put it in vertex form. But ultimately, if you want true vertex form like this, notice there's nothing in front of that x. I don't mean cross it out. I mean there are things you're going to have to do with it. And I'm going to be sure to do them if those problems pop up. In this case, factor the 3 out of this binomial and then square it. Those are the two things I'd most prefer to want to do in that situation. Okay, let's look at the example of writing a transformed quadratic function. Let the graph of g be a vertical stretch by a factor of 2 and a reflection in the x-axis, followed by a translation 3 units down of the graph of f of x equals x squared. So take the parent function and do vertical stretch of 2, that sounds like a. Reflection in the x-axis, that sounds like a, means make it negative. And then a translation 3 units down, that sounds like a k, subtraction. So write a rule for g and identify the vertex. So reflection in the x-axis, vertical stretch of 2, a is going to be negative 2. Negative for reflection, 2 for the stretch. K will be negative 3. This is the part we're going to add at the end of it. They're going point blank with this thing here. Notice that h had no translation cases, so h is 0. That means you kind of leave it be. And x minus 0 is the same thing as x. So negative 2 multiplies in front by the x squared. Adding negative 3 is minus 3. There's your equation. And it's in vertex form. It's in vertex form. Just because there's no x in parentheses with the minus 0 doesn't mean it's not in vertex form. It's also in standard form, if you know anything about that one, but there it is. And the vertex is at 0, negative 3. H is 0, k is negative 3. There's another method at play. I'm probably not going to be using this as much now that we know what vertex form is, but this is the one we were doing out of section 2.2 at the time, where we would multiply negative 2 by the output and then plug it in right there and then subtract 3 from the new output and do all that. I think I want to get deeper into the actual vertex form aspect. I think this is going to hit home a little better. The book preaches it, so I'll be using that more often if it seems right. All right. Another example of writing a transformed quadratic function. Let the graph of g be a translation 3 units right and 2 units up, followed by a reflection in the y-axis of the graph of f of x equals x squared minus 5x. Oh, interesting. So this is not in some form of vertex form. This is one where you might want to do more of that other method. This is one where you might want to do the transformations based off the result of exactly this here. Okay, I think I do prefer it with this one, and I like that they show it now. So h of x is this transformation of f of x. You take f of x, and within the function, we subtract 3. That's the 3 units right. Remember, opposite of inside the function. And then we add 2 units up outside the function. We keep it the same, but the function is x squared minus 5x. So anytime there's an x that exists, plug in x minus 3. Anytime an x exists, plug in x minus 3. And outside the function, you add 2. Then they distribute some stuff. X minus 3 quantity squared is x squared minus 6x plus 9. And then minus 5x, negative 5 times negative 3 is plus 15, and plus 2. You have x squared, negative 6x minus 5x is negative 11x. And 9 plus 15 is 24, plus 2 is 26. That's where they're getting that value. They skip some steps, but they say simplify, and that's it. They say then write a function. Wait, what do they do? Oh, followed by a reflection in the y-axis. We're not done. Then we do the reflection in the y-axis, which is flipping over, changing all your x's to make them negative. Now, this parabola was not on the y-axis, so flipping it will not necessarily be the exact same. If it's off the y-axis, flipping it moves it over. So with this one, you plug in negative x into your function. Negative x squared is still x squared, but negative 11 times negative x is plus 11x, and that will change the appearance of your graph. They didn't graph it, but it would change the appearance. It would change it from this side over to this side somehow. Okay, example 5 on modeling with mathematics. Let's take a look at the problem and see what to do with it. The height h in feet of water spraying from a fire hose can be modeled by this guy right here, where x is the horizontal distance in feet from the fire truck. The crew raises the ladder so the water hits the ground 10 feet farther from the fire truck. Write a function that models the new path of the water. So, now I actually don't know what it says they raised the ladder, but it says 10 feet farther from the truck. I don't know if they mean upward. They probably do, but we'll see. So understand the problem. You're given a function, so that's the model. X is horizontal distance. Oh, 10 feet farther might be outward because they also have horizontal distance. But you're given a function that represents the path of water spraying from a fire hose. You're asked to write a function that represents the path of the water after the crew raises the ladder. So you analyze the graph of the function to determine the translation of the ladder that causes the water to travel 10 feet farther than write the function. I still got to follow this a little bit more because the crew raises the ladder so water is 10 feet farther. Okay, so what you basically do is you got to find out when this thing originally would have been. Oh, I have a graph right here. Find out where the function would have originally been hitting the water. This is one where using the graphing calculator is probably right. This isn't in vertex form. It's a really weird decimal thing. Use your graphing calculator, let it graph itself, and find out, trace where it would have hit the ground to begin with. At the time, we traced that, and it looks like it would have hit the ground 50 feet from the fire truck. Now, they're going to raise the ladder, and eventually it's going to hit 10 feet farther. What's 10 feet farther than 50 feet? 60 feet. So we're going to have to change this function so that when we get a value of 0 here, when we plug in 60, we're getting a value of 0, I guess I should say. I wonder how to say that. But using graphing calculator here, let's see. By observing that h of 60 is negative 23, there it is, we got to figure out that we have to raise the fire truck 23 feet up to get it to travel 10 feet farther, because apparently at 60 feet, it's negative 23. So there's a point on here that's, again, 60, negative 23. And I'm observing this at the same time with you guys. I want to make sense of the problem, and it totally does make sense. So I guess we're not doing too much on the algebra realm. We're really letting the calculator take care of it for us. And you can double check and see that when you make it 23 feet higher than 25 at 48, you get 0 out as a result. So this changes the equation from a 25 here to a 48 here because we need to make it 23 higher. Okay, that's the end of the lecture portion. It was still 22 minutes long. I was hoping it would be shorter, but it seems like there were still a lot of things to cover. So let's start with the vocabulary and core concept check, and then we'll do numbers 3 through 49. Okay, complete the sentence. Number 1, the graph of a quadratic function is called a, or not an, it's called a parabola. Parabola, it's a U-shape. Number 2, vocabulary. Identify the vertex of the parabola given by f of x equals x plus 2 quantity squared minus 4. Remember, the actual vertex form looks like a times x minus h quantity squared plus k. I'm going to have to bring that up 1 or 2 times here. The x minus h, this is x plus 2. That means we're subtracting a negative 2. That means h is 2, or negative 2. And the minus 4, we're adding negative 4. That means that k is negative 4. Your vertex is at hk. Your vertex is at negative 2, negative 4. And we're going to get really used to that pretty much right off the bat, right off the front, for plotting vertexes to make our graphs from that form. So I'm going to go ahead and get started, guys. It looks like the first big set of problems we are going to be doing some graphs for. So get ready with your PDFs and stuff if you want to print these things out, your own graph paper that you have. I think I'm going to go off the tall graph paper and make that happen. And I'm going to go ahead and get started with this problem set right now. Yeah, ha ha ha. So I'm going to already get this copy-paste job. Oh, I got the wrong graph already set. I'm going to get this copy-paste job ready right there. Oh, you can't see something here. Give me 1 second. Where is this guy? Where you been? Where you been, buddy? Come back. Where are you? There you are. Hello. We're here. Okay. I'm going to go ahead and get started. And I guess for you to see it all, well, generally, I don't think it's going to be at the very bottom of the graph for that part to matter. But we're going to start with problem number 3. And in sets 3 through 12, we're going to describe the transformation of f of x equals x squared represented by g, then graph each function. I'm an either-or kind of guy when it comes to do I describe first or graph second, vice versa. And keep in mind, although we describe translations last, I do translations first because I start by plotting the vertex. Anyway, for g of x, let me put it over here. For g of x equals x squared minus 3, let's copy it down. It says graph each function. They don't say to graph the parent function. So I'm not going to graph the parent function each time, but keep in mind, it's generally 1, 1, 2, 4, 3, 9, 4, 16, and then a reflection of that over here, blah, 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 and then you draw that graph, okay? That's the parent function as a general whole. Okay, let's go ahead and describe this guy first. This is just one thing from that x squared. We're going to translate 3 units down. Only spelled correctly. Okay, we're going to translate this thing 3 units down. So yeah, you know, that's where my vertex is, right? Vertex is at 0, -3, like that. And it's a translation of that original parent function. Remember what I just said, 1, 1, 2, 4, 3, 9. All that stuff applies, only they're all 3 units lower than before. So if I start from the vertex, I can go from here and do 1, 1, 2, 4, 3, 9, 4, 16, 13. I think that's 13. 5, 25, I can't fit, but I'm going to go plot this on the other side. And it's a pretty quick reflection. If you understand what's going on, I'm keeping the same height, and I'm counting the distance away from the axis of symmetry that I got to go. The reason these graphs generally take so long is the curve I got to draw. And I apologize if my curves end up not looking good eventually after like 50 graphs, even though I don't have 50 problems, but you know what I mean. Even after so many graphs, I kind of go like, well, there's only so much dead time I can fill by talking, and I got to keep moving with the problem. Just you make a better graph than me, please. So yeah, listen, it takes this original parent function right here, and it translates it 1, 2, 3 units down. Not just the vertex, but every point in relation to that vertex. And that is our number 3. All right, let's go to number 4. On number 4, we have, oops, I got to move it. G of x equals x squared plus 1. And it looks like all these problems begin with just translation. So you're really just getting the practice in translating and really getting that 1, 1, 2, 4, 3, 9 aspect down, if you know what I mean. We're really getting that part worked out, and I want you to follow along very carefully with me. And I think you'll then start to make sense of reflections really easily, and then stretches, hopefully, in time. So we're translating 1 unit up, and maybe you're already along with me on it. Maybe you did this in IM2, and you're like, it's clicking. I get it. We're following along. Good, good, good. So 1 unit up. That's a k value of 1. We're 1 unit up. Let's go 1, 1. Let's reflect it now. 2, 4. Let's reflect it now. 3, 9. And 4, 16. Now, before I move on to the next problem, I'm going to speak out loud about how I'm doing this so fast. And then how you can, especially if you're using the same graph as I am, the same graph axes as I am, maybe you printed it out. You're like, how are you counting that fast? Well, here's the thing. I'm not counting fast. I'm calculating fast. I'm adding. So I don't know if you notice, because there aren't numbers on here, and I apologize. Maybe I should amend these so that they do have them. But notice these bigger hashes right here at 5, 10, 15. And I've done this so many times that I know that the top is 17, or it's 2 up from 15, right? So just kind of keep that in mind, right? Now, when I do like 1, 1, 2, 4, 4 up isn't too far away, but 3, 9, I'm not counting 1, 2, 3, 4, 5. Even if I did count, I would count from 4, right? 5, 6, 7, 8, 9. However, I'm not counting up 9, I'm adding 9. From what number? From 1, because my vertex is at 1. So when I say 3, 9, I'm doing 3, and when I say 9, I'm doing 1 plus 9, which is 10, and 10 is this hash. 4, 16, what's 16 up from 1? 17. 17 is the top of the graph. So I'm not counting. Okay, I'm calculating. So I hope that you understand how I'm doing that so fast, in case you were actually curious, and maybe you can do the same thing, because you count too long, these graphs are going to take forever. Just be thankful we're not using a table on top of it. And thankful we're doing the reflection pieces instead of also recalculating those. This one says, on number 5, g of x equals x plus 2 quantity squared. That is inside of there. That gives you a vertex of -2, 0. By -2, that means we're translating to the left. Translate 2 units left. And that is the transformation of this guy. So we are taking our graph. And you know what I'm probably going to do on some of these? Because, listen, all of these graphs, once I make the perfect graph, I'm going to do it. All of these graphs have the same exact vertical stretch, all that kind of stuff, right? 1, 1, 2, 4, 3, 9. Let's see if I can make this the perfect graph. And literally, guys, I'm going to copy and paste them. I hope that's okay. For my sake, this video would end up being longer than it needs to be. You can pause the video as needed. Maybe you're not doing as many problems as I am. So I want to, and maybe you already know how to do it now. You're like, I get this set. So let me get a really good looking curve, or best as I best as I can try and manage here. Just go 1 point at a time. Pretend like it's kind of curving alongside there. That was pretty good. Look at that. And then I'm just going to copy and paste this one each time, and I can place it within each graph. Oh, no, 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 no. And you know what? I'll just start it at the parent function as well. So give me a second. Let me just kind of get this one settled. I'll get it set on the next page even. Let me get this here. Copied. Boom. And then I'll revert where we were. Okay. So, cool. Hopefully I'll get this ready for all the future problems here, all right? All right, that was number 5. Okay, number 6. On number 6, we have g of x equals x minus 4 quantity squared. Yeah, guys, we're only the 4th problem in, right? And this is going to add a lot more time if I don't actually just get things done. So, here we go. First, let's start by typing out what this transformation will be. We're going to translate 4 units to the right. Okay? If you still don't understand that aspect, it's because I got to plug in 4 for x to make this thing 0 again. I got to make them 4 larger. That's why we go 4 right. All right, I'm going to paste this guy. Here we go. Paste it, and then I got to lock in the graph axes themselves so I can move this. I take my parent function and translate it 1, 2, 3, 4 units to the right. Boom, there's my graph. You see, I moved the vertex 4 units to the right, sure, but I moved everything 4 units right. They all follow. That's the graph. Is that okay? I'll let you kind of pause because I'm going to move on to number 7, but hopefully that's okay. All right, number 7. And by the way, this is a tremendous waste of paper on my end, not utilizing all that. I'm sure there are a lot of other things I could say, but quite the waste. Quite the influx of problems as well. I wonder where they're going with turning into x minus 1 squared that number 6 didn't do for me already. So g of x equals x minus 1 quantity squared. Now we're going to translate just 1 unit to the right. Sorry, there's a thing in front of me. I am a much better typer than this. I have to reach around something, and I don't know which key I'm pressing. Anyway, translate 1 unit right. Let's go ahead and take this same thing and ba-doop-da-doop. Let's take it and go. 1 unit to the right. That is the quickest graph I've ever made. Okay. Yeah? Number 8. There are only so many ways I can say 1, 1, 2, 4, 3, 9. Know what I mean? And honestly, I'm actually not miffed at plotting the points. It's drawing the curve on this stylus thing that's really troublesome. I'd even be fine doing it on paper. It's doing it on the stylus thing that's really tough. It's not so easy. It's really cumbersome. All right, this time we're going to translate 3 units left because the plus. And same-ish. Take this thing and go. Let's see if I can arrow it. 1, 2, 3. Okay. Still hitting all those points that I want them to hit beyond that. All right, number 9. Now, numbers 9 through 12, they're still translations, but now we get to translate 2 portions of it, vertical and horizontal. So this is a little bit more of talking in terms of the vertex thing. With this one, maybe I start with this one by not doing the copy-paste thing. I'll actually just start by bringing this one in normally. Let's talk about the translation. Let's do the graph thing with respect to it and see if we're still okay with it. We're going to translate 6 units left and 2 units down. That also means that the vertex is at -6, -2, right? When I do these graphs later in the future, I'm going to say the vertex is at -6, -2. I'm going to plot that vertex at, boom, -6, -2. And from here is where we do all that stuff, right? The stretch factor is 1, so we just go the standard 1, 1, 2, 4, 3, 9, 4, 16. And yes, -2 plus 16 is positive 14. And then we go and draw the graph from there. So I'm going to make it kind of a quick graph. But yes, from there we do that. That's the idea. I will be doing the copy-paste thing and translating them for probably the rest of them. But there's still your graph. You still got it down. And listen, if something goes low enough, I'm going to fit 525 on there. Okay? I'm going to fit what I can fit. All right, let's go to number 10. This one I won't be able to fit 4 over 16 up. But this one is g of x equals x minus 9 quantity squared plus 5. I really like that the book is now entrusting that, hey, you can do this without a table. I kind of apologize that in section 2.1 I was doing it without a table the whole time, I guess, but it was still a long video for me. Translate 9 units right and 5 units up. Honestly, I feel like in this way now people will be more prepared for doing what you're supposed to do with it here. Oh, shoot. Hold on. Let me try that one more time. That because what I did in 2.1, you're more prepared for the fact I was going to do it now. Okay, this one's going to be interesting. I'm going to go 9 units right and 5 units up, and we're going to get some cutoff here. Even if it's already pre-made, you know, you might not make all these points. So let me do it more like this. You know, you see where it cuts off on the screen there. Let me like erase it as if I didn't have it, right? It didn't exist. And I only go as far as I'm able, right? Maybe just that one point and I draw the arrow. It loses the feeling of symmetry, and I get it, I do. But that's what you draw. That's still the symmetry that we still utilize. And also, also in this realm, right, too, right? I wouldn't fit that last point on the graph, the 416. So my graph would just look like that. Doesn't look great, but that's technically what I would be doing on my graph. That's just, I plot as many points as I can fit. I wouldn't just do these 2 points and just draw that and just leave it be, right? I'm not going to do it like that. That's ridiculous. I plot what I can fit. I plot what I can fit, and that's what I can fit. Okay, let's go to number 11. Oh, did I? Yes. Okay, I did describe it. All right, number 11. G of x equals x minus 7 quantity squared plus 1. Yeah, they really want to make sure you know how to do this well, and I hope that I'm going slowly enough for you. And you can please pause your video or slow me down that you're playing catch up. Maybe you're ahead of me. Maybe you're going faster than I am. Translate 7 units right and 1 unit up. This might have a little bit of cutoff, technically, from what the original graph would have been. Let's see. Let's go 7 right and 1 up. So we go over to 7 right and 1 up right here. So technically, I could totally fit that one. I think the last point that I would theoretically be fitting, probably, I would probably put it there, knowing me. But you might not. You might say, I run out of room at this 10, really, and I'm just going to kind of cut it off right there, do what I can. Maybe that's your look of it, but that's still the look of it. Remember, this is just the window range. The graph still goes forever. That's just all you could fit. The last one, number 12, I have to go to the next page for it, but number 12, ooh, this one's really going to be cut off, but which direction do we go? Why didn't they just go down 10? G of x equals x plus 10 quantity squared minus 3. Now, this is the limitation of the graphing window, right? This is just based off what I'm able to provide. So translate 10 units left and 3 units down. This one will really struggle to show what that left side of the vertex looks like, or on the left side of the vertex looks like here. So with this one, we'll be at 10 units left. Goodness golly gee, right there. See, it's running into my problem now. That's a problem. That's an issue. So all this goes. I'll probably do that one just to indicate it's got to go back up, right? I don't just draw an arrow at the bottom. Otherwise, that's a problem. I got to show that it's going up. So I'm going to do that. Still just as icky. I wonder how the book does it, like as far as answer key stuff. I wonder what theirs look like. Unless they shift their window. We don't have that luxury. Even on my my normal scaled graphs right here, I don't have that luxury. It goes as far left as -10. So I'm not going to double. Oh, you know what they might do? They might double their scale or something, right? And if they go farther, like 15 or something, I will double my scales, but not for now. Okay, let's go to numbers 13 to 16. Analyzing relationships. In 13 to 16, match the function with the correct transformation of the graph of f. Explain your reasoning. Okay, I think I did something similarly to this before with absolute value functions, and what's nice about something like this, here's what I'm going to do. Here's the original graph of f. It's not the parent function x squared. It's just some random graph. Looks like it's translated right and up. You know what I mean? And what I'm going to do with it is I'm going to keep this one ready to go on the side. And I'm going to copy and paste. Oh, let's see. I don't know if I should call this 13. I think on the last set, they gave us the graphs, and then we did a match. So here's what I'm going to do. I'm going to find what the answer is beforehand, and then I'll line it up for you. Otherwise, this doesn't really work. Okay, I believe number 13 is C. Let me copy down the problem first. Y equals f of x minus 1. What we're looking to do, it says explain your reasoning. So I am going to describe what we do here. You take this function, and the minus 1 inside the function means we're going to translate 1 unit right. So what I'm going to look for is I'm going to find a graph that is 1 unit to the right of this one. The one that seems, oh, actually it might not be C, it might be A. It might be A. The one that seems to be 1 unit to the right of this graph, it does look like it's A, is A. When I copy paste it and transparent this thing and line this thing up correctly, you can see a match, not a match of the graphs, but you can see that it looks like this graph here is this graph but translated over to the right. How far is, not really our concern because there's only one of them that only translates 1 unit right. It doesn't translate up at all. So this is the one that seems to match. That seems to be A, graph A. And that would be my answer there. So I kind of have to find the answer first, and then I'm going to line it up for you after and just kind of make that work that way. I hope that's okay. Okay, let's go to number 14. And we have y equals f of x. And then outside of the function, there's a plus 1. And the outside the function idea means it's going to be vertical. It's going to be vertically related, and it's a vertical translation. We're going 1 up. So to go 1 up from this graph here, remember here's the original f of x graph. Which one looks like it's this but just 1 higher? I think that one's D. So let's copy paste D, line that one up, and see how that one looks. I'm going to copy paste. I'm going to transparent it. I'm going to shrink it to match size. And look at that. This new graph here takes that one and goes 1 up. And I'm finding a part that corresponds, like the vertex. And I'm just showing that. That looks like it's going 1 up. It looks like it's D. Let me write that. Translate 1 unit up. I'll say 1 up. And that is D. So this graph matches with D or the transformation graph matches with graph D. Okay. Let's bring this over. Let's go to number 15. By process of elimination, we'll know which one 16 is going to be. But 15 and 16 take on 2 different things, a horizontal and a vertical translation. So this one is going to say y equals f of x minus 1 plus 1. This actually takes both of what we did on numbers 13 and 14. It's going to translate 1 unit right because what you see here, and 1 unit up because what we see here. This might be what was graph C. I haven't checked what the last one is, but 1 unit up. So it looks like this one might be graph C. What was graph B is different, and graph B looks to be the opposite of what we're doing there. So let's copy paste graph C. Let's see that it wasn't supposed to be one of those other ones as well, and compare it to that. So when I shrink it, kind of matching up, take a look at where the vertex was and now is. It looks like it goes, right and up. It did maintain the same height or the same horizontal displacement, so that clearly looks like it's going to be graph C. And then last one, by process of elimination, the answer must be B, but let's play with that as a for sure. Let me just do it down here. Number 16, we have f of y equals f of x plus 1, and then minus 1 on the outside. Which means now we're going to translate, and these are good problems to look at because then you have selections of answers, you get to practice function notation, the whole rule of that vertex thing doing what it's doing. Let's look at that graph B as a final one. This looks like this should be a translate 1 unit left and 1 unit down. B seems to show that. B also shows that window cutoff that I had for the other graphs that I just made on the previous set. And look at that. We were here. Now we're here. We're going 1 left. We're going 1 down. That seems to be B. Translate 1 unit left and 1 unit down. That's B. That seems to address those 4 questions there. So I had to mix, match, pick them out. I'm sure you had to do a little less than that, but we still had to explain it, and there we have it. Okay, let's move forward. Numbers 17 to 24 describe the transformation of this represented by G, then graph each function. The difference on these ones is now we're not doing, well, we are doing a translation on 23 and 24, but we're not doing so much on translations anymore. Now we're really focused on reflections and stretches and compressions or shrinks. Some are vertical, most are vertical, some are horizontal. All right, Let's start with g of x equals negative x squared. Now with this one, this is technically outside the function. If it was inside, like number 18, you'd see it in parentheses in some sort of way. That would be that. This one's a reflection in the x-axis, which means you're flipping over the x-axis. The y values turn negative instead of what they were on in the positive realm. Now let me take... I'm not going to take my parent function thing I did anymore. I can't do that copy-paste thing I did because it was always faced upward, 1, 1, 2, 4, 3, 9 style. We don't get that luxury anymore. So now I actually have to graph these as they are. So this one, this one here, we do start at the origin still, and we're going to go 1, 1, 2, 4, 3, 9, but downward. So 1, 1, can you see this? Okay. 1, 1, 2, 4, 3, 9, 4, 16. You're doing this with a table, would have done the same thing. You would have squared 1 and then made it negative. Squared 2 and then made it negative. Remember, the negative happens after you square it. That's why the reflection goes in the x-axis. That's why y is affected from it, because the squaring happens first on these ones that affect output. If it's one that affects input, it happens before you square it. That's why we have to counter what it is that we're doing as a result of that. So there's that graph. Beautiful as it is. I still had to draw it, and we are done. Okay, number 18. Now, number 18 is an interesting one, and I believe we saw 17 and 18 in the example set, but doesn't mean we can't practice it ourselves. This is negative x quantity squared. Now, there's an interesting thing that I would love to do with this actual thing, and I'll show you what it is in a second. We're going to do a reflection in the y-axis. Now, I want you to imagine what it means to reflect in the y-axis. To reflect in the y-axis means to flip a U-shaped graph, 1, 1, 2, 4, 3, 9, in both directions, over, and you get the same graph out as you always had. The original parent function and this reflection in the y-axis are the same graph, which means I could take my old graph, copy, paste it, and I'd be done. But this is 1, 1, 2, 4, 3, 9. See, here's I'm reflecting right now. Right now as I graph these, reflect over, boom. And this reflects over to boom. So it's still the same thing that we had. It's still the same thing that we had as the original parent function. This is the same. And let me prove it to you that it's the same right now by doing something to this guy. If we were to argue vertex form, I could argue this is vertex form. If we were to argue vertex form here, I'd lose because there's something in front of x. You know what I can do with this function? I can square it. What is negative x squared? That means negative 1 times x quantity squared. I'm overdoing this, but I'm going to show this later. This is negative 1 squared times x squared. Negative 1 squared is 1, x squared is x squared, and that's x squared. Wow, that's a lot of work to just go from here to there. That would have been a lot easier. But g of x equals x squared. Guess what? That's the parent function. That's the parent function. But I did want to show you this. I wanted to show you separation of, a property involved, squaring a negative turns positive, that kind of stuff. And this is what we get back to. So it is the same thing. This is not the first. This is the first. It's not the last time you're going to see me turn a horizontal component, especially on stretches and shrinks, into a vertical component. Horizontal component's gone. This is now a 1 stretch factor. Let's go to number 19, and let's look at g of x equals 3x squared. Now this 3 is outside of it. It's a vertical stretch factor like a. This is a vertical stretch by a factor of 3. Vertically stretch by a factor of 3. Now I might slow this one down just a little bit because this is the first time you're seeing with me in description form, actually teaching it, a vertical stretch factor. You do have to keep in mind what we've been doing each time. 1, 1, 2, 4, 3, 9, right? Now we're vertically stretching everything 3 times bigger. Instead of 1, 1, 2, 4, 3, 9, etc., you got to triple those y values, not the x's. It's a vertical stretch. Vertically stretch. We got to triple the y's. 0 squared is still 0, times 3 is still 0. 1 squared is 1, times 3 is 3. 3 times taller than 1. 2 squared is 4, times 3 is 12. So it's a vertical stretch. It's 3 times taller than it would have been compared to the parent function. 3 squared is 9, times 3 is 27. I can't fit that on this graph. This is as best as I can do. So I'm going to go ahead and just draw this one. It's the vertical stretch. That is the graph. And that's how we did it with that rapid speed, which is nice. And I would still do this even if there were translations. I would still go 1, 3, 2, 12, things like that. 1, 1 tripled, 2, 4 tripled, etc. All right, number 20. Number 20 is also a vertical stretch, but it's not a stretch, it's a shrink, it's a compression. So this is g of x equals 1/3 x squared. We're going to take that graph and we're going to vertically, the parent function, and vertically compress it, vertically shrink it by a factor of 1/3. So instead of multiplying everything by 3, we're going to multiply everything by 1/3, which means divide everything by 3. The vertical parts by 3. See how good you are with this? Instead of 1, 1, 2, 4, 3, 9, etc., we're going to divide 1, 4, and 9 by 3. 1 divided by 3 is 1/3. 4 divided by 3 is 4/3, which is 1 1/3. I know it's not your favorite. 9 divided by 3 is 3. That one's fine. And I'll give you a heads up on these ones. I would probably recommend that you only plug in numbers that are multiples of 3 outward. As in, 6 squared is 36. 36 divided by 3 is 12. Those are the only ones that will land on integers. If you want to do other ones beyond it, oh, let's see. 9 squared, 81 divided by 3 is 27. I can't fit that on here. I'll do the other ones in between. 16, 4 squared is 16 divided by 3 is 5 1/3. So here, 5 squared is 25 divided by 3 is 8 1/3, right here. So you can plot some. That was 6 squared. 7 squared is 49. 49 divided by 3 is 16 1/3. So I'm always going to try and plot. Oh, what did I do here? Give me 1 second. I'm always going to try and plot as many points as I can fit. You, on the other hand, might want to stick with the integers, but make sure it still gets that smooth curve basis and don't miss out on some just because it's a fraction. Okay. This is probably one of the better looking graphs you can make if you can get all those other points within. You get some width on it, and you get a bunch of points for it to go through. It's a curve. It's a curve. It does sharpen. But there you go. Nice looking graph. Okay, number 21. G of x equals 2x quantity squared. Now I have a lot to say on this problem because of the differentiation in it and what we can turn it into if you want to. I really want to hit home what you're allowed to do on a question like this. First of all, by nature of its current appearance, this is a horizontal component. Now, is it a stretch or a compression? It's a compression. So you horizontally compress it when I want to call it B. When this thing's more than 1, you got to compress. This is by a factor of 1/2. You take your number, you basically take its reciprocal, right? You invert it. Horizontally compressed by a factor of 1/2. Now, as far as that graph goes, it's going to look like this. Think about what we're doing. Horizontal compression. Remember the whole 1, 1, 2, 4, 3, 9? That 1, 4, and 9, and 16, those maintain. Now, instead of 1, 2, 3, and 4, take half of those. 1/2, 1, 1.5, 2. So instead of 1, 1, it's, well, here's 0. Instead of 1, 1, it's 1/2, 1. It's a horizontal shrink. Instead of 2, 4, it's 1, 4. Instead of 3, 9, it's 1.5, 9. That's half of 3. Instead of 4, 16, it's half of 4, 2, 16. That's the horizontal compression of this thing, and you can reflect those points over like this. I don't like plotting these ones as much. Kind of hard to do. That's why I like the other one even more, despite its fractions. This one is kind of, we'll make it work. Whoa, already starting off very weakly there. This is going to be very tough for me to get going. Now, that's one way for us to do it. Nothing wrong with it, but I'll tell you what, it's a rarity. Vertex form does not show horizontal things. In fact, how many of these problems have horizontal? This is our first horizontal stretch / compression one, right? Are they going to follow up with a bunch after? The next one is, and after that, no. For all I know, there are only 2 problems. Yeah, there was a reflection on number 18, but that didn't do anything. For all I know, these are the only 2 problems. I don't know if there are more. Guys, horizontal stretches and compressions are not a big part of it. They're a part of it, and we got to talk about them. But you can also change it. And I'm going to show you right here. Here's what you could also do. I just did it from a previous problem. You remember number 18? Let's do it here. 2x quantity squared means 2 times x quantity squared. That means, and I'm probably overstating this, I'm sure you know this, 2x squared means you square the 2, you square the x, right? But I'm going to write it. You square the 2, you square the x. X squared is indeed x squared, but 2 squared is 4. This becomes 4 times x squared, which is 4x squared. Okay, what am I saying about that? That means instead of describing this as horizontally compressing by a factor of 1/2, you could have also described this as vertically stretch. by a factor of 4. And you would get the same graph, which is the cool part. You might not be getting as many points this way as you would have here because you got some half points on these ones. But take a look at these points here if we vertically stretch by a factor of 4. Here's the 0, 0, right? What does vertically stretch by a factor of 4 mean? Instead of 1, 1, 2, 4, we do 1, 1 quadrupled, 1, 4. Boom, that's that point. Instead of 2, 4, it's 2, 16. Boom, that point. It's still the same graph. We missed out on the little half points, but it's still the same graph. So that's really what I want to bring up with this thing right here. You can transform those horizontal ones into vertical ones. A horizontal compression is a vertical stretch. And I hope you get why a compression of one is a stretch of the other, right? That makes sense. Narrowing the graph also means taller. Widening the graph also means shorter. So that's that concept, and I'll make sure to throw it out whenever we're able to. Now, number 22, listen, 22 is just like 21 with one giant exception. There's a negative on the outside. Means we also do a reflection of this. I wish they did a 1/2 inside of there so we could talk about that, but they didn't. So this is the problem. G of x equals negative 2x quantity squared. Now keep in mind, if you wanted to do a simplification of this by squaring that, the negative doesn't get squared, but this does. This would be negative 4x squared. So it's one of two things that you can write on this. You can either horizontally compress by a factor. Let me kind of copy and paste this problem over. I want to keep this exactly as was. So sorry about this. I'm going to kind of just do a lot to it. Ignore what I just wrote before because I'm going to modify everything here. So we're going to horizontally compress by a factor of 1/2, but we're also going to reflect. It's a reflection in the x-axis. And it's a horizontal compression by a factor of 1/2. This is probably messier than I wanted to make it, but I want to just, save time. And I don't know if I'm going to be doing so in the process. If I really wanted to save time, I would just pause the video. But, pause, change it, and resume. But I want a negative there, which means a negative here. And all I got to do this graph is what? Flip it over. I hate when I group it. It kind of gets smaller. But I'm just going to flip it over and put it like that. So, guys, it's the same graph but flipped over. Okay? Whether you're talking about vertical stretches, whether you're talking about horizontal compressions, it's still just a flipped over version of what we had previously, okay? So there's that one, 1, 4, 2, 16 downward, etc., or 1/2 over to go down the 1, 4, 9, etc. Okay, that's number 22. Let's go to number 23. Now, number 23 has an interesting fraction of 1/5. It's not a common one that we see, but we will deal how we do. And this is also one where I might state, hey, if you're not in the, what's the phrase? In the camp. If you're not in the school of thought of using the fraction versions of stretch factor stuff, only go multiples of 5 out. Choose 5, choose 10, etc. Anyway, we're going to this is a vertical compression by a factor of 1/5. Followed by a translation 4 units down. Keep in mind the translation 4 units down happens afterward, and that is indeed a k value because it's outside of the function. It's not inside the parentheses or anything like that. So this one I got a graph for myself. This one, I'll be honest, I don't know if I need the tall graph for it. So I'm not going to, well, you know what? I'm going to be able to fit actually quite a bit here. I'm going to get that 10 out on this one. I definitely will here. All right, take a look at this. We're going to start 4 units down. And this is the first one that does a translation with the stretch factor. So I'm going to go 4 units down to begin with, and everything I do will be in relation to my vertex. Now from here, I could do the 1, 1, 2, 4, 3, 9. But we're going to take a fifth of 1 and 4 and 9. So let me start with, if I go over 1, I go up 1/5, right? That's kind of hard to actually do. If I go over 2, I go up 4/5. That's still less than 1. It's still right there. And then I do 9/5. So those get a little tricky. Let's do some integer ones that you might feel comfortable with. Let's go over 5 and let's go over 10. Because if I go over 5, I go up 25/5, right? I go up 5. I go over 5, I go up 5. So this is where I end up going there. It's an integer. Maybe that's a nice one actually hit and I reflect it across. I go over 10. 10 squared is 100. A fifth of 100 is 20. So I go up 20 when I go over 10. What's nice about this is I'm at -4. -4 plus 20 is 16. I can fit it on this tall graph. I can fit it right there and right there. Now you can see this might be hard to draw this curve through just those points like that. So I'm going to still keep plotting other points just to get you in that, camp of using fractions if you'd like to. Over 3. Okay, 9/5 is 1 4/5. So boom. 16/5 is 3 1/5. We have 25/5 there. Okay. 36/5 is 7 1/5. 49/5 is 9 4/5. So 8, 9 4/5. Whoops. So that's 10 right here, right? So this is 10. 64/5 is 12 4/5. So 10, 11, 12 4/5. And 81/5 is 16 1/5. So 11/5. No, 12/5, 13/5, 14/5, 15, 16 and... Hold on. Did I say that right? 81/5 is 16 1/5. Did I count something wrong? 16 would be, I guess right here. 16 1/5 is right there. Okay, that's a lot of points plotted, but you know what? That might make for a much smoother curve. At least I have some points to go on to right there. I hope I did all my division and mixed numbers and stuff right. It almost feels like I'm going straight, but that's the benefit of having so many points to hit. Whoops, just a little under. But that's still cool, right? You can get all those points. Imagine that you actually had to plot all these points using a table. See, what I'm doing is I'm using the translation thing. I'm using fractions. I'm using the parent function behavior, 1, 1, 2, 4, 3, 9. I'm just dividing my numbers by 5. So I'm working it out from there. All right, there's the graph. There's the notion. And then number 24, which should be a much easier graph for me to handle because it's a half, not a fifth. That means a lot less points to fit as well. So number 24 is g of x equals 1/2 times x minus 1 quantity squared. This one might look more like vertex form to you because now we have one in parentheses. So it's whatever. All of them are vertex form. Well, I take it back. 18, 21, and 22 were not vertex form because there was a number in front of the x. This one doesn't have one in front of the x. It's in front of the x squared. That being said, there are two things we're going to do. We're going to vertically compress by a factor of 1/2. And then we're going to translate. Is it 1 unit down? No, it's 1 unit to the right. Now, as far as my graph goes, I'm going to translate 1 unit right first because everything I do will be in relation to said translation. And then I'm going to apply that vertical stretch factor. So 1 unit to the right, vertex is at 1, 0. The 1/2 idea of this, instead of over 1 up 1, it's over 1 up half of 1. Over 2 up half of 4. Let's reflect these. Over 3 up half of 9, that's 4.5. Over 4 up half of 16, which is 8. Over 5 up half of 25, which is 12.5. Over 6 up half of 36, which is 18. This tops out at 17, so I'm going to kind of just plot one more up like that. That can be my 18. All right, good looking graph. Hopefully you heard what I said for my numbers and you can make sense of what I'm getting from those ones. And there's the graph. I'm very, very glad that the book is refraining from table usage because now I can do this freely and say, we're expecting you to do it as well without a table. Let me pause for a sec. I need to take care of something. Okay. Number 25 and 26. Error analysis. Describe and correct the error in analyzing the graph of f of x equals negative 6x squared plus 4. Do we have to graph it? I don't think so. Okay, they state the graph is a reflection of the y-axis. Wrong. Well, it technically could be, but there's another one. And a vertical stretch by a factor of 6, right, followed by a translation 4 units up the graph of the parent quadratic function, right. So the only incorrect portion is the reflection of the y-axis. This, they stated a reflection in the y-axis, which isn't wrong, but they didn't state what it actually is when it is actually a reflection in the x-axis. Now, the part of this that is maybe troublesome for you guys is you might know what the graph visually is supposed to do. Flip it over here. but you might accidentally state reflection in the y-axis. So I appreciate that the book brings this up. Why might you state reflection in the y-axis? Because you hear y, you think up, down. You're like, hey, reflect it, change the y's. Let's reflect in the y-axis. But this is the x-axis so that we're reflecting over, right? This is the y-axis here that we're reflecting. So it's one of those things that you might be very aware of what you're supposed to do, but you might just think wording wrong. It's just like, you know how the y-axis is also the equation x equals 0? And the x-axis is the equation y equals 0? We get some of those things mixed up, even though we have all the correct intention in what we're supposed to state. This is probably them meaning the right thing. They're like, yeah, you flip it over this way, right? Y-axis. That's an x-axis reflection. That's the problem. All right, so anyway, that's the correction on that part. The rest was correct. Number 26, the graph is a translation 4 units up, followed by a vertical stretch by a factor of 6, reflection in the x-axis. So all the words on number 26 are correct. The order's wrong. This is where this part gets a little tricky, and I'll show you what it is that I mean about this, but they stated the translation first. Oh, geez. The translation before the stretch and reflection when it should have occurred last. Here's the thing, and here's the tricky part about this, right? The tricky part is because when I graph, I translate first. But you have to keep in mind, when I translate, I affirm my translation there. I keep my point where it is. You know, when I do a graph, and I'll go ahead and do the idea of what they stated versus what I would do. But when you read their statement says it's a translation 4 units up. Keep in mind, they're thinking of the parent function. They're saying, I already have my parent function drawn right here. Boom, 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 and 416. All that kind of stuff, right? I have this graph. It's going to look a little sloppy, sorry. But I have this graph here, and they're thinking, do this to it. Looks terrible. They're thinking, take this guy, translate it 4 units up. 1, 2, 3, 4. Then they say, vertically stretch this by a factor of 6. That would mean make it 6 times taller, right? Oh, I can't actually stretch it. Oh, well. But they'll say make it 6 times taller. If they make it 6 times taller, they don't do this. 6 times taller here, 6 times taller there, and graph that. No, you know what happens? Even this gets 6 times taller right here. This would turn in from 0, 4 to what's 6 times taller? 0, 24. This would go all the way up there. And then, oh, by the way, reflected over the x-axis. You know where it would now go? 0, negative 24. It would totally flip over and go down there. The rest of the graph would also be 6 times taller and upside down, but every point goes with it. So mentioning translation first means once you translate the vertex, everything you do after also affects the vertex. That's why we have to actually state stretch it first, because you know what 0 times 6 is? 0. It keeps the vertex on the origin. And then if we reflect it, you know what 0 times negative 1 is? 0. It still stays right here. And then we translate 4 up, and you know what 0 plus 4 is? It's 4. So we get it in that spot. Now, when I translate first, I translate with the understanding that I'm locking that vertex in place. And what do I always say? Every point I plot thereafter is in relation to my vertex. So everything is going to move up 4 with it from where it would have been after a stretch, down after a stretch and reflection. So I move up at 0, 4 as my vertex, and I affix everything from here. I go stretch factor of negative 6. I go over 1, down 6 from here. I'm doing it out of order with the understanding that the plus 4 is already applied. These things already got a plus 4 applied to them. They're already 4 up higher than they would have been. And over 2 down 24, I can't probably fit it, but over 2 down 24, and then I draw the graph. So I graph out of order. I acknowledge it. I graph out of order. You cannot state it in that order. So how should you state it? State it in left to right order. I would recommend it. It's okay if you state the stretch and then the reflection, as opposed to reflection then stretch, but I just recommend that you do it in order. Reflect over x-axis, vertically stretch by a factor of 6, translate 4 units up. The way you graph it may be different, but the way you state it, go left to right. And you know what else is nice about this vertex form? F of x equals a times x minus h quantity squared plus k. A is alphabetically first, then H, then K. Even if you don't remember left to right, go alphabetically, or vice versa, whatever. You know what else is nice? You know, vertex form doesn't seem to show what I call that B, that thing that should be inside of here. And I'm going to start talking about this more if it comes up in future problems. You still can say left to right. Do your vertical stretches and reflections, then horizontal stretches and reflections, then your horizontal translation, then your vertical translation. You can state it like that, and it's still alphabetical. And I know they don't happen to mention it as the letter B. I do. But yeah, you can use that as well. Totally works. Totally works. I know I overstated on number 26, but these are good error correction questions. These are two really good questions that are things that we should speak to students about, that students would make mistakes on. And if you were assigned these problems, I hope that you absorbed everything I just stated. If not, please ask questions down below. I always encourage that you ask questions. Numbers 27 to 30. Describe the transformation of the graph of the parent quadratic function, then identify the vertex. They never state graph. So unless I feel I need a graph for this, I probably will not graph one. So f of x equals 3 times x plus 2 quantity squared plus 1. Describe it of the parent function. Remember, the original is just equals x squared, so what's everything doing in comparison? It's at this stage that you can probably thinking in terms of vertex form. I mean, it is vertex form. And they do ask you to state the vertex, but it's probably at the stage you probably start doing that, right? I state right now that the vertex is at -2, 1, which also means, as a description, will translate 2 left and 1 up. But the a value being 3, of course, is the vertical stretch, and that's the one we have to mention first. So I wrote a equals 3. I don't think that's a requirement of the question, but the transformation is a requirement, and I want to make sure you know both parts. Even though we plot the vertex first, we first mention the stretch. I just mentioned this on number 26. So there's a vertical stretch by a factor of 3. Then we translate 2 units left, and hopefully you know why it's left instead of right, and 1 unit up. So that's what we got to do on these problems here as far as mentioning them. We got to do the description and identify the vertex. Okay, let's keep going. Number 28. Now, number 28 is full-on vertex form. There's everything under the sun that we got to kind of talk about as long as it's... And listen, look, none of these are horizontal stretches or compressions. And as I reiterate, they aren't as heavily featured. Vertical ones are. Vertex form is like this, so we're going to have to make sure we note that. All right, a is -4. That means two things to us, which is what? Reflect in the x-axis, vertically stretch by a factor of 4, and don't say -4, by the way. The negative had to do with the x-axis thing. Then we'll talk about the vertex and what the translations are from there. The vertex here is at -1, -5, which means we are going to translate 1 unit left and 5 units down. Okay, so those two things involved get the description. There's the vertex, yada, yada. We are good. We are good, aren't we? Number 29. Make no mistake, this is vertex form. If you have trouble acknowledging or identifying the vertex form thing here, note that you do have a vertical translation, but there's no horizontal translation. If there's no horizontal translation, think about how your vertex started at the origin, 0, 0, and the h value is still 0. So you could rewrite this in vertex form as -2 times x minus 0, quantity squared plus 5. I know a lot of people that would prefer this appearance, but you'd have to come up with it on your own, right? Now, anyway, the a is the first thing I want to talk about, the -2. Then we'll get to the vertex, which is at, indeed, 0, 5. If you need this portion of it to make sense of that, by all means, you do you. You do need to know what it means without it, though. Anyway, we're going to begin with a reflection in the x-axis. Then vertically stretch, and it's still a stretch, by a factor of 2. And then we translate just 5 units down. You don't say 0 units right. You just translate 5 units up, excuse me. Okay. And I hope I'm not going too fast on these. I hope over the course of the problems that we've had so far, we're really starting to feel out vertex form. I wouldn't be surprised if right after that, they just say graph these next ones. They don't talk about transformations or parent functions. They just say graph. I don't know. I kind of hope they do those because I really want us to feel comfortable with them. Now we got f of x equals 1/2 times x minus 1 quantity squared. And that's it. So the A value is 1/2. Oh, I didn't box anything on this one. Hold on. Boom, 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 boom. The A value was 1/2. That makes it a vertical compression. So vertically compress by a factor of 1/2. Oh no. I'll just kind of leave it like that. And then we got a vertex. No. We got a vertex of what? There's no K value. So if you're thinking in addition to it, you're adding 0, right? So the vertex is at 1, 0, and it is 1, not -1. That does mean we're translating 1 unit to the right, and that's it. Translate 1 unit right. Okay. That's 27 to 30. Let's box it. They did not ever say graph, so I won't. Maybe we're graphing on the next set of problems. Okay, numbers 31 to 34. I don't think so. I don't think we're graphing there. Numbers 31 to 34. Write a rule for G described by the transformations of the graph of F, then identify the vertex. So it just really sounds like we're like going in circles here, only we're just adding more as we go. I think it says see examples 3 and 4, so they're really following the example bases of things. They're really talking about vertex form now. They're really shouting vertex form in our face. So the original f of x equals x squared. I'm not going to copy that info down, but vertical stretch by a factor of 4 means a equals 4. If we're thinking about a, h, and k, a is 4. There's a reflection in the x-axis. Oh, a is -4. Okay. Followed by a translation 2 units up. That's the k value. K is 2. So as far as our f of x equals a times x minus h, quantity squared plus k, you could write it like that, and simplified, it's -4x squared plus 2. I'd really prefer to see that as a final simplified after what you do. It's in vertex form, technically. Is that all you do? Oh, then identify the vertex. The vertex is at 0, 2. Whether you see it based on its form or you did it based on the translation. If they say translate 2 units up, you're translating the vertex 2 units up from the origin. So as simple as that. Let's move to number 32. Number 32, vertical shrink by a factor of 1/3. That doesn't change the fact that it's still a, and a is still 1/3. That's kind of nice that they accompany us with that. And a reflection of the y-axis. Now, listen, I showed this in one of the questions. I don't know which one. I think it was the error analysis one. I'm going to throw out this B to you guys. Like that. I know they call it an A. I need a different letter for it, though, because I already have an A here. B are horizontal stretches, compressions, and reflections. This mentions a reflection in the y-axis. That is a horizontal reflection. Now, that being said, there's no horizontal shrink or anything else, so I'm going to call it -1. I'm going to do a lot with this stuff and talk about how this changes things or not, but it says followed by a translation 3 units right. Now, this is quite interesting. H is 3. So let's get into what this should look like as a raw form to start with. By the way, that would mean k equals 0. I'm going to bring those ones up. If they don't talk about it, I guess I'll write it like that. So this is going to be f of x equals 1/3 times -1 times x minus 3 quantity squared plus 0. Now, as far as a simple simplification here, -1 is also just the same thing as throwing the negative sign out there. So this is 1, whoopsie, hold on. And there's no plus 0. I don't really need that, right? Here's one form of what you could write. It's a little rough around the edges, though. It's a little rough around the edges. This is a form of what you could write, though, and I could see a problem being represented this way. The negative is the reflection in the y-axis. And it is, I need to stress this as well, it's factored outside of the x minus h. I keep saying I don't want anything in front of the x. Nothing's in front of the x, but something's in front of the x minus h, which is b. But here's where squaring a negative should turn your thing positive as well, though, right? So whether you treat it as a -1 that's being squared, remember it's multiplying by that, or just squaring the negative, it's in front of that. I can square both this, and x minus 3 quantity squared I'll leave as x minus 3 quantity squared, but squaring a negative turns it positive. That means I can just have a +1 multiplying by 1/3, which means it's 1/3. This means x minus 3 quantity squared like that. I know this gets a little tricky, and I know to some people they'd understand reflecting that thing across the y-axis means there's no change to it. Notice they said followed by a translation 3 units to the right. You didn't translate 3 to the right and then reflect it. You reflected it and then translated 3 right. That means the reflection didn't change anything. And it didn't. It didn't change anything. Squaring a negative turns it positive. Little tricky, but they mention horizontal components. And they're doing more horizontal components on these ones, and I'm going to keep talking about them in this form. I'm going to bring this down. I'm going to keep talking about, I need to identify the vertex. Did I do that on the previous problem? I did. Okay. I need to identify the vertex on this one, which is at 3, 0. Okay. But I'm going to bring this thing down because it looks like the next two questions, what the heck? That's an old copy. The next two questions talk about horizontal components. These are where the horizontal components exist, guys. These are where the horizontal components exist. They didn't really bring it up like this because this isn't, you don't need this for vertex form. I'll show you how we can change it. Number 33. Oh, look, the original graph is not x squared anymore. Okay, this is going to take a little bit. F of x equals 8x squared minus 6. A little bit of a change. We're going to horizontally stretch by a factor of 2. That is b. Now the b value is not going to be 2. The b value is going to be 1/2. Do opposite. Do opposite. Some books write it as 1 over b. I think one of my old sets of lecture videos will actually have that as 1 over b. So you can work off of that. So I don't know if you recognize that from some of my old videos, but I might even have it like that so you know to actually flip it over. Horizontal stretch by a factor of 2. And a translate, oh, this is a tough question. And a translation 2 units up, followed by a reflection in the y-axis. So let's start with this. Let's do the reflection in the y-axis afterward. It's going to change a little bit, guys. There are a few things in this problem. Actually, the reflection in the y-axis might not really change anything because there's no horizontal translation and the original graph isn't horizontally translated. But it could have been trickier. Anyway, let's start with this, guys. Let's first call this thing g of x, okay? I'm gonna work this out a little bit differently. Now, oh boy. We're going to take whatever f of x was, we're gonna multiply the inside by 1/2. That means we're gonna replace x with 1/2 x, and then we're going to add 2 to whatever we do. Okay? So, we're gonna take this function, which is 8 times, we're gonna turn x into 1/2 x. That's squared. There's a minus 6, and we're going to add 2 to it. That means we can rewrite g of x as 8 times 1/2 x squared minus 4. This is one version of an answer that you can do. There's a vertical stretch by a factor of 8. There's a horizontal stretch by a factor of 2. What I would prefer, the book might prefer it as well, you've seen them talk about it, is you square the 1/2. You square the 1/2, and then you multiply it by the 8. 1/2 squared is 1/4. The x is still squared on its own, and 8 times 1/4 is 2. This simplifies to 2x squared minus 4. I think you would agree this looks significantly better. You take the horizontal stretch and turn it into a vertical compression on the original function that you already had. The translation 2 units up is being applied. We're all good there. But the vertical stretch is only being applied to just that one portion of it. Okay? All right. Now, there's still another part to this. We're now going to take this new b that we got to do, which is -1. There is a reflection in the y-axis. Now, will this change very much? Not really. Because now, what I'll call h of x, I don't know, I think I've been calling the other ones f of x. This, we're going to take this and turn it into -x squared, right? We take the g of x, and we're doing g of -x. h of x equals g of -x, like that, right? I probably should have written that. So, all right, so 2 times -x squared. -x squared is x squared. So what do you get? You still get 2x squared. So 2x squared minus 4. Ha, that was a lot. Now, it didn't change anything by reflecting afterward, only because there was no horizontal translation at all from the original graph or with our new transformations. If there was, it would have changed something. It would have turned like an x minus 3 into an x plus 3. It would have changed something. Yeah, there it is. Okay. Vertex. The vertex is at 0, -4. And I'm feeling very confident in my answer with all that in mind. Okay. All right, let's go to number, oh, something popped up. Let's go to number 34. Still have a little bit to go. F of x equals x plus 6 quantity squared plus 3. We're going to horizontally shrink by a factor of 1/2 and a translation 1 unit down followed by a reflection in the x-axis. Okay, the followed by, maybe we should save for the end because we got to do these other parts first. We might do the g of x, h of x stuff that we did before. Horizontal shrink by a factor of 1/2 means flip that 1/2, turn it into a 2. Our b value is 2, opposite of what we do. Translation 1 unit down is a k value of -1. H is 0, a is still 1. That stuff doesn't change. So our g of x, we're going to take our f of x and make that x a 2x. And we are going to subtract 1 to whatever we had originally. So we're going to take g of x equals, we're going to replace x with 2x. It becomes 2x plus 6, quantity squared, plus 3 minus 1. And that becomes 2x plus 6, quantity squared, plus 2. Now there's more I'd like to say on this problem, and I likely will momentarily, as far as simplifying. For now, for a moment, I'm going to leave it because we're not at our final stage yet. Followed by a reflection in the x-axis. Reflection in the x-axis is, or a, is now -1. So my new h of x, I don't know why I changed the colors back to black, but we're going to take our g of x, whatever it was, and make it negative. We're going to flip it over. So h of x, whatever g of x was this whole thing. It was 2x plus 6, quantity squared, plus 2. That whole thing we're going to make negative. As far as distribution of that negative goes, the negative will sit outside the 2x plus 6 quantity squared, and then we'll distribute the negative into the 2. We'll get -2 like that. This is an answer. It's not my preferred answer, not by a long shot. Here's why. Let's say you said this was the answer, which is, it's fair, it works, but here's the problem. We have to name the vertex, right? What's the vertex? If everyone who knows their vertex things would say, they're going to say -6, -2. I can't write that. -6, -2. You know why I wrote it in red? Because it's wrong. The vertex is not -6, -2. What? But Mr. Robinson, you flip the 6, right? You flip this and you keep the sign. -6 is not the x value. It's not the h value of vertex. The way vertexes work is it's the minimized bottom, or the maximized top. This graph's upside down. It's the maximum top. It's the value that you want to plug in for x that gives you 0 inside of here. It's the one that when you square it, it minimizes your change in x. The problem is this b thing. Remember how I wrote this form before? Remember this? You notice how b is factored out here? If you want to reveal your true h, you got to factor out b. Truly, I don't want b in here, period. I want to square it out of there. But to square it out of there, I have to factor it out first. If you want to reveal your true h value, you got to factor out that 2. Not from the squared quantity, but from this binomial. I want to turn this into h of x equals negative, and then I have, hold on, x equals negative, and then inside I have 2 factored out, and you have x plus 3. Quantity squared minus 2. Remember when this was a horizontal shrink? Remember the original graph? The original function was x plus 6 quantity squared plus 3. This vertex was at -6, 3. And never mind the fact that this thing flipped over and all this stuff. This thing was at -6. It horizontally shrunk by 1/2. This -6 has to get 1/2 shrunken smaller. You know what half of -6 is? -3. That is here. That's indicating to you what the vertex is. This is a valid answer that I prefer more. It's still not what I prefer most, but it's what I prefer more because this reveals the true vertex. You know what the true vertex is? -3, -2. Right now, our a is -1, our b is 2, our h is -3, our k is -2. This is the proper one here. This still shows the horizontal shrink. It still shows the reflection after the fact. This shows k units. Remember, we went 1 unit down and then we reflected, so it's kind of weird. You know what my favorite answer is though? I still want to square that 2. I still want to make it my a value. I don't want to look at it as a horizontal shrink by a factor of 1/2. I want to look at it as a vertical stretch by a factor of 4. I got to square 2, make it 4, multiply it by the -1 right there. Oh, something just popped up. And then I turn this into just that normally. Here's my favorite look of this answer. This is fine. Heck, this is, this is fine as long as you know how to get your vertex. From this one, I'll get the vertex. From this one, I'll get the vertex. This is my favorite answer, guys. This is my favorite answer of them. I'm sure you'd agree if you could get to it. This would be the easiest one to graph and all that as well. You deal with one kind of stretch or compression. Make it the vertical one. Yeah, the most recent problems have dealt with horizontals. They have. But you can still turn them into verticals, and that's my intent to doing that here. I just did. So hopefully, the solution guide is truly guiding you to proper solutions and what you can do, and hopefully you're understanding what's best for you. But let me tell you what, the vertex is not -6, -2. Don't be fooled into thinking that just because there's a +6 there, it's -6. Don't forget the fact, we did a horizontal shrink, right? We turned it from -6, 3. You shrink it by a factor of 1/2, your vertex is now going to be -3, 3. Granted, some other things changed, right? We made this 1 down and we flipped it over this way. But don't forget that stuff, right? That stuff is applied. Okay, let's keep moving forward. Let's do numbers 35 to 40. Match the function with its graph. Explain your reasoning. Okay, I feel like here I'm just going to copy paste the graph that's on there. So we're going to find it, okay? G of x, and we'll explain reasoning by all the information that we have here. Whoops, that's a 2. So this first example, so this is us practicing vertex form. They have the graph for us, but we'll explain it. So with this one, the vertex will be at 1, -2. We're going to find that one. And then there's a vertical stretch factor of 2, okay? So we're going to find the one with the vertex of 1, 2, 1, -2. There may be more than one. That's 1, 2. No. Here's 1. And that's the only one. Looks like the answer is going to be C. Now, is it a vertical stretch factor of 2? 1, 2, 2, 8. I believe it is. This answer will be C. So here's the graph. Let's copy, paste it, shrink it down. There it is. My reasoning is the stuff that you see in the listing there. It applies the vertical stretch and the vertex. All right, let's go to number 36. Number 36, g of x equals 1/2 times x plus 1 quantity squared minus 2. The vertex of this one is at -1, -2. We can hunt that. There's a vertical compression factor of 1/2. This means it'll be a wider looking graph this time. Let's first find one with this vertex. Not A. B works, and F works. Now, when you look at F versus B, what are some things that call out versus one and the other? F is flipped over. That to me tells me it's not it. B also shows that further width. Okay, there's over 1 up 1/2, over 2 up 1/2 of 4, which is 2, over 3 up 4.5, that's 1/2 of 9. It looks to be B. So B shows that vertical compression as well as anything else, and there is going to be my answer to that one. That is B. Okay, there's the vertex and 1, 1/2, 2, 2, etc. Hopefully this really gets you to understand how I do these graphs in general as well. Number 37. G of x equals -2 times x minus 1 quantity squared plus 2. Okay, let's start with the vertex, because that's how we would graph them, right? 1, 2. And there's a reflection. You flip it over. Whenever I say reflection, I'm referring to x-axis. I mean this kind of flip. You reflect it. Your vertical stretch factor is -2, is 2, right? 1, 2 is the vertex though, right? So let's find a 1, 2 vertex. Here's one, and here's one. A and D. Now, which one is it? Well, it's the one that's flipped over, right? Now, by the way, A might have a vertical stretch factor of 2, but it's not flipped over, so it's not A. We're going to find an equation that's just like this. I'm going to spoil it. We're going to find another equation that's this, and that's going to be A. I think, assuming that's a stretch factor of 2. This, however, is D. So let's copy paste that one. Oh, I guess it's going to have that mark on there, sorry. But there is the graph of D, and there's my explanation. It's mostly the flip over, right? That flip over really was a selling point of that. Obviously the vertex. I mean, listen, you don't have to start from the vertex. You can say which ones are flipped over, D and F, and then just, and then go by the vertex. It's up to you. Okay, number 38. 38's close to A. I don't think it's A. There's one difference. Number 38, g of x equals, listen, a lot of these are the same kind of looking graphs. A lot of them have, none of them have a stretch factor of 1. I just noticed that. All of them have a stretch factor of 2 except for one of them. So g of x is 2 times x plus 1, quantity squared plus 2. Now this vertex is at negative 1, comma 2. It does have a vertical stretch factor of 2, but a lot of them have 2. So which one has negative 1, 2? It looks like E and only E. So I'm going to go with E. It is an upright graph. It's got the stretch. I expect all those things with it. This one, whoopsie, I just hit the wrong button. This one seems to fly in that way. That's E. All right, let's cross out the ones we found so far. We found E. I don't know what we found. E, D, B, and C. We're looking for A and F now. All right, number 39. It's the other upside down. If we're playing process of elimination, it's the other upside down graph, right? But g of x, probably F because it's not A. G of x is negative 2 times x plus 1 quantity squared minus 2. This has got a vertex of negative 1, negative 2. It's going to be a reflection, and it's got a vertical stretch factor of 2. By the way, I want to state this right now. I am describing this backwards. Keep that in mind. Well, sort of. I said the vertex is this. I didn't say translate this, so maybe it's not backwards. I stated the vertex. Anyway, it must be F. Negative 1, negative 2, flipped over. Yep, it's going to be F. Let's copy and paste that guy. And hopefully we're getting a good feel of what we're doing as far as plotting vertexes, identifying them, that whole flip the sign for H. This is the letter F. And the last one must be A, and it must be that one equation that I said before. So let's check it out and see that it all worked out the way we wanted it to. Number 40. No mistakes left over. G of x equals 2 times x minus 1 quantity squared plus 2. So this is a vertex at 1, 2. It's got a vertical stretch factor of 2, as most all of them had. This is A. 1, 2, there's a vertical stretch over 1 up 2, over 2 up 8, I'm sure. I'll just copy paste that one. We should be all good. Taken care of, right? Now, that doesn't mean, therefore, you can graph them all, right? There are other, maybe you're not good on the horizontals. Maybe you're not good on vertical compressions, things like that. But hopefully you're really feeling it. I really want you to feel at the vertex. I really want you to know 1, 1, 2, 4, 3, 9, and what we do with the stretches to make them happen. I hope vertical stretches you're okay with, and flipping over. Other parts, we got to practice. All right, we have 9 more problems to go. We're on number 41. In exercises 41 and 42, justify each step in writing a function g based on the transformations of f of x equals 2x squared plus 6x. Well, they want us to fill in these blanks. I'm just going to copy and paste that whole text box thing so I can just write inside there. I've done that with proofs in the past for IM3 videos. I'm sure this is fine that I do it here as well. Okay, I don't know what they want us to do here yet. Translate 6 units down followed by a reflection in the x-axis. So h of x equals f of x minus 6. Wait, what are we doing? Justify each step in writing a function. We're justifying why we're doing it. Why we're doing it or stating what we're doing? I actually don't know what we're supposed to do. Do we say subtract 6 from the function? Let me think about that. So when we have this here, I would say, let's see, what are the other steps? So I know how to do these steps. The 6 units down and subtract 6, then we're substituting the function in there. This, by the way, is this function here. F of x equals 2x squared minus 6x. They're substituting the function in after. Let me just say this out loud. We're subtracting 6 from the function. We're substituting the function in. And then we're following the reflection. We're multiplying this thing by negative 1. We're substituting the new function in, and then we're simplifying. So I guess that's what we're doing. I think we're saying subtract 6 from f of x. I don't know if that's justified, but that's actionable. That's telling you what we're doing. Then we're substituting function in, that's the 2x squared plus 6x substituted in, the minus 6 is still here, right? Now we're going to do the followed by the reflection. So we're going to the reflection means multiply h of x by negative 1. Okay, give it a new output. We substitute the function, h of x function, and then we simplify. I don't know if that's expressed right. It's kind of a weird set of statements. I know we didn't do examples off these. I'm going to say that's what we do. I don't know for sure, but that seems like seems good. All right. Number 42. Oh, same bit. So number 42, let's copy paste it. Whoa. Is it enough to love? I don't want to get a copyright strike by singing Avril Lavigne songs. All right, let's see. A reflection in the y-axis. Okay, agreed. So first thing is we multiply our input by negative 1. See, when we multiplied f of x by negative 1, that was our output. Multiply input by negative 1, our x. It's justified. Now we're substituting negative x for x. This is how function notation works. Substitute negative x for x. By the way, sub doesn't mean subtract. It means substitute. For x, use parentheses. And then we simplify. Okay? Negative x squared is x squared. 6 times negative x is negative 6x. So we simplify that. This is followed by a translation 4 units right. 4 units right is we're going to subtract our input right to the right. We do subtraction in the input. We subtract, I don't want to write sub again. Subtract input by 4. I don't know if this is doing well. We substitute x minus 4 for x in this new, by the way, we're taking our h of x equation and we're doing that, right? We're taking this one. So instead of 2x squared minus 6x, it's 2 times x minus 4 quantity squared minus 6 times x minus 4. And then once again, we simplify. Now they do the simplify stuff very fast. Let me remind you of how this thing works. Because you might say, how did they get from here to here? You might not be asking that because you might just be trying to answer the question. After you saw me write that, you might be done and moving on. Let me remind you how this works. X minus 4 quantity squared is x squared minus 8x plus 16. And this distribution will happen as well. Negative 6x plus 24, right? And then we distribute that. So a lot of people probably don't remember. Number one, you can't distribute the 2 in first. Number two, x minus 4 squared isn't just x squared minus 16 or x squared plus 16. It's x squared minus 8x plus 16. And so we get this. Now let's see if that all worked out. 2x squared is here. Negative 16x minus 16x is negative 22x. And 32 plus 24 is 56. So that is this right here. That is simplification at its finest. They skipped steps, but I don't think they want to write those steps as far as it. All of those steps are simplification steps. So it's justifiable. Okay, let's move forward to number 43. Aha, we did do word problems, or we did do examples with word problems before the kangaroo. The jump, or the function, h of x equals, let me write this, models the jump of a red kangaroo. So 43. H of x equals this. Ooh, it's in vertex form. X minus 14 quantity squared plus 6. It models the jump of a red kangaroo where x is the horizontal distance traveled in feet. Boom, boom, and h of x is the height in feet. Kangaroos jump high, guys. That means a 6-foot height. When the kangaroo jumps from a higher location, it lands 5 feet farther away. Write a function that models the second jump. Okay, this is where graphing calculator stuff is probably going to be employed, especially when it comes to this, especially when they don't expect us to know where x-intercepts land on certain parts here. So I'm going to use the graphing calculator with this in mind. But let me tell you a little bit about what I do know on this graph. I don't know its y-intercept, but I do know that with this graph here, it's got a vertex, and you should know this too. It's got a vertex of 14, 6. That means 14 over and 6 up. This thing hits its peak right here, right? Now, I don't know where the kangaroo starts from. Maybe this is modeled in such a way that it actually has an x-intercept right here of 0, 0. That might make sense. It jumps from the ground, It goes 14, it launches 14 feet outward and 6 feet in the air. I don't know if kangaroos do this or not. That's a huge half of a jump. And then it goes all the way back down. And if it does truly, maybe this is actually hitting at 28, which is double 14, right? Maybe it's doing that. We need it to go 5 feet farther away from whatever it is. But this is my idea of what the graph would be. It would be an upside down graph because the negative. It would be hitting a maximum height here and going back down. So let's go ahead and use the graphing calculator. Let's type this information into it and let's see what it does. I actually anticipate a 0, 0 unless it's jumping from a, what did it say it jumped from? Jump of a kangaroo, Oh, from a higher location. Never mind. It doesn't actually jump from the ground. So I was actually wrong on that part, but it doesn't matter. I'm going to let the calculator do it. But it's going to still hit that peak. So kangaroos must jump farther than they jump higher. It must have not actually jumped 6 feet since you jumped from a higher location. So x minus 14 quantity squared is here, and then plus 6. Now what you're going to have to do here, see if I just hit graph, it'll graph, and it'll show a whole model. That didn't seem to jump from a higher location. That seems to be from the origin. Oh, when it jumps from a higher location, it goes 5 feet farther away. I take it back. Okay, so I think it does actually hit at the origin there. Let's check the table for sure. Not quite the origin. I think they had to round to the nearest hundredth on the negative 0.03, but I think we're assuming origin. It's jumping from the ground. Anyway, the problem here is our graph, not a good window range, right? We don't actually even really care about these quadrants over here. I don't really care about that part of x. I don't care about this part of y. And I really need to stretch x out more, right? You saw what we needed to do before. We needed to probably get it out to about, let's say, 40 feet, maybe. Now, this will change the scale of what it looks like. It doesn't quite look like this normal arc because x is now compressed. That's fine. We just need to see the points for what they are here. We need to see where this thing is hitting the x-axis. So I need to find, this is where you can either scroll over until you find it, but there's also some certain functions you have here. It's called calc. You can go to the calc section here and you can find the zeros. Okay, you can find zeros. Now, this is kind of weird, left bound, right bound. Left bound means what's the furthest left I want to search for my zeros. Right bound, I got to go to the right of this value over here. And then when it says guess, it means make sure you're close to it. I will be. And it's going to find this one right here. This is when x is at 28.142136. It's kind of a weird number. It's kind of a weird number. And that's where I said about the 28 as well, right? That's where I said it was going to kind of hit. Now, that is the original 0 here. I don't know if I'm not saying I'm doing it right or wrong. I don't know if what I'm doing is appropriate to what we need, though, because it was the number 28. It's rounded. It's a rounded one, but, or excuse me, it's a weird one. I'll just write that. The x-intercept it's around 28, but it's 28.14, I'll just say 14 feet. Now we need to go 5 feet farther out, right? So this number plus 5, that'll be about 33.14 feet, okay? We need to do something to our graph so it goes 5 feet farther out. Now, for us to make it go 5 feet farther out, we need to, I suddenly don't remember what to do. Oh, we need to find what the y value is when x is this number. So this is going to be a little bit tricky, right? I have to go back to the calculator and remember this number here. I'm going to write it down, but just keep it in mind, 28.142136. I'm going to get as close as possible to the actual value. Even if I just wrote 28 or 33, I'd be fine. So I need to go to my table, and I'm going to turn this thing to ask so I can substitute the number 33.142136. I need to figure out how much lower this is below. Okay, it's supposed to be about 5 feet lower. I need to go how much lower it goes below the ground level so I can shift my whole thing up that much higher. So when it's that, the y value is, hold on, I'm writing some stuff on my thing. At 33.14, we're at negative 4.99 about. I'm sure we're supposed to say it's about 5. I know. And I'm sure we're supposed to say it's about 5. I'm being particular to start with. We'll round at the end. That means here that we need to, here's that ordered pair. That means for us to land on this point, we need to shift upward 4.99 units. So our new function, that was h of x, we'll call this one k of x for kangaroo. K of x needs to take h of x and it needs to add 4.99 to it, right? It needs to add 5 feet. So that's the idea. I'm sure when it comes to an answer key, they're literally just going to say add the 5. I don't know that for sure, so I'm not going to do that, but that's the idea behind this thing. We're going to add 4.99 to this. What was our original h of x? This guy right here. So k of x is going to take negative 0.03 times x minus 14 squared plus 6, and we're going to add 4.99 to it. I'm just going to round to that. So that means our new function is going to be negative 0.03 times x minus 14 squared plus 10.99. Apparently, to go 5 feet farther out, you need to go about 5 feet up. Is that true for every kind of jump? No. Is that true for every part of this jump? No. That was just actually coincidence that it was like that. And it wasn't exactly 5, mostly because of the rounding, but this would be the function. Case in point, let's see if that actually works. Let's go to the graphing calculator one more time. Let's turn the 6 into a 10.99 and see the result of everything's now translated, basically 5 feet out. That means now it can go, in this case, 5 feet farther out because we saw where it would land. So when I go to the graph, you'll see it. We can't see the top anymore, but let's see what that bottom is now. That bottom, it's going to be rounded, but that bottom should be at about 33.14 feet. Let me just move over down to it this time. But normally we'd find the 0 right there. You can't really tell. But yeah, it's about that 33. It's about that number there that it's hitting the crosshairs on it. Anyway, that's the problem. It's a little interesting because you got to use the graphing calculator. You got to be particular with their numbers not being exact. The example had exact numbers. So anyway, let's see if 44 is anything like number 33 or if it's just a different tricky kind of question. The function f of t, let me write it, f of t equals negative 16t squared plus 10. That sounds like gravity and a vertical displacement. Models the height in feet of an object t seconds after it's dropped from a height of 10 feet on Earth. The same object dropped from the same height on the moon is modeled by g of t. So one's Earth, one's moon. Negative 8/3. So this is gravity on the moon with respect to feet in seconds, basically. It's a little lighter. It's a lot lighter. So this is Earth, and the other's moon. Earth and moon. Describe the transformation of the graph of f to obtain g. From what height must the object be dropped on the moon so it hits the ground at the same time as on Earth? Okay, those are two different questions. Let's start with the first one. Now, first of all, the graphs. The graphs would basically look like this. The plus 10 for both of them would both start right here. Negative 16t squared. The parabolas would kind of go like that, right? It's kind of actually the vertex. But negative 16t squared might go pretty sharp down like that. This side doesn't really matter to us because this is time advancing forward. At some point it hits the ground. On the moon, as time advances forward here, it's going to hit the ground a little bit later like that because it's a more compressed, it's a more vertically compressed stretch. There's more vertical compression, but it also means there's more horizontal stretch. And I think that's what we want to talk about because we don't want to stretch the 10. We want to keep the 10 the same way. I think we want to talk about horizontal stretching. Describe the transformation of the graph of f to obtain g. So from f to g, we want to stretch this thing out. Okay? We want to stretch it. Whatever the multiplication is to make negative 16 turn into negative 8/3. So how do you do that? Negative 16 times what number equals negative 8/3? You got to divide both sides by negative 16, which means times negative 1 over 16. Negative 8 over negative 8 over 16 is 1/2. Negative times negative is positive. You got 1 times 1 on top, 3 times 2 on bottom. That equals 1/6. So you got to horizontally stretch. Oh, hold on. I don't know if it's a horizontal. I don't know if that's the... let me first say vertically compress because these are vertical. So let's say we vertically... This might be a tougher statement than I thought, because these are not vertical stretches here. You know what I could do? I could see where they land and take the vertical stretches there. I'm going to try this two different ways. I'm going to do what I'm doing here. It's a bit of a vertical stretch there, or compression, but the problem is it changes my 10. And I don't want to say vertical, do this, and then translate up. That's kind of weird. I want to make it horizontal. The problem is this. These are vertical things here. So let me kind of rechange this, and then I'll talk about these landing spots, but I got to use the graphing calculator for that. I'm going to turn these, I'm going to keep the negative in front, but I'm going to turn that 16 into a b value, something inside. 16 is 4 squared. So if I turn it into 4t squared plus 10 like that, then this is a true vertical compression. It takes something and it vertically compresses by a factor of 1/4. Remember, that's how that works. It's opposite of. Now, that's by taking the square root of 16. Here's the problem. I got to take the square root of 8/3. It's not going to be a clean number. G of t is negative square root of 8/3 t squared plus 10. I could do things like rationalize the denominator, simplify the radical. This is probably me way overdoing the problem, but I want to make sure that this is done right. 2 root 2 over root 3. If I rationalize the denominator, I get 2 root 6 over 3. So I'm going to turn this into 2 root 6 over 3. And this is where we got to do the comparison truly. You know what I could have done? I probably could have taken the 1/6 and taken the square root. Probably could have taken the 1/6 and taken the square root, and I'm only now realizing that. But that's okay. We live and we learn. We live and we learn. So let's see if it's the same thing. Let's see. The square root of 1/6 is the square root of 1 over square root of 6, which is 1 over root 6, which if you rationalize the denominator is root 6 over 6. So let's see if we get root 6 over 6 doing this right here. I'm going to be dividing 2 root 6 over 3 by 4, which means times 1/4. And yes, 2/4 reduces to 1/2, and 1 root 6 times 1 is root 6, and 3 times 2 is 6. Okay, that is the same thing. So dividing and then taking the square root obviously is the same thing as taking the square root and dividing. So I need to horizontally stretch. So here's the thing. I need to horizontally stretch. This is a tough problem. F of t by a factor of root 6 over 6 to make g of t. Now, another way I could do the problem is by comparing the two intercepts of these and dividing, one by the other, right? I could do this one divided by that one. The only problem with that is they would be on the calculator with a lot of decimals, and dividing it would only show me a decimal equivalent of root 6 over 6. I would never get the true root 6 over 6. So I'm probably not going to do it that way. But this is what I got to first do as far as that goes, because it's not just 1 over root 6, right? That's to go from f of t to g of t. That's what they wanted, right? Describe the transformation of graph of f to obtain g. Yes. Okay. The only problem with that, you know what though? That's backwards, right? Because, oh, that's backwards. You know why? Remember, this is 1/4, and this is the reverse of that. So I actually got to flip this. This isn't root 6 over 6. This is actually, I have to flip it. It's actually 6 over root 6. 6 over root 6, and when you rationalize that, you're going to find out this is root 6, equals 6 root 6 over 6, which is root 6. So it's actually root 6. It needs to be bigger. Root 6 over 6 is a number less than 1. I need the number to be greater than 1. It needs to be wider, and that's going to make that happen. I forgot, we flip these. We don't flip them inside of here, but as far as the stretch goes, we flip them there as well. This is a hard question, guys. Anyway, here's the first part of it. I don't know how many of you guys were assigned this question. This is me clearly seeing it for the first time, and hopefully working it out in a way that kind of makes sense to what we're doing. I know I did a lot of scratch work, and I'm not even done with it. But me processing is trying to figure out how to get it right, and I think so far I am. at least for that. That's a lot, though. That's a lot. Now, what I could have done was what I did to begin with. I do 8 root 3 divided by 16, but then I got to do 2 more things. I got to take its square root, and I got to flip it. So, still a little tough. Okay, there's a second part. From what height must the object be dropped on the moon so it hits the ground at the same time as on Earth? This is where I got to decide if I should be using the graphing calculator or doing it in a different way. But here's the thing. To drop it the same thing as Earth, you obviously have to make it lower, right? Lower, lower, lower till, boom, it hits the same place as there. So what we have to do, I'm trying to think if I should use the equation. I'm trying to think if I should use the equation or if I should use the graphing calculator. I could use the graphing calculator. I know I can. I'm trying to decide if I should use the equation and if I can talk through it. I need to... Yeah, I think I need to use the graphing calculator in the sense that we're probably not solving these things algebraically together. I don't mind solving it algebraically. Like, this is still number 44, right? So we have, let me rewrite these. F of t, these are fine to solve algebraically because they're easy quadratics. Basically, if I set this thing equal to 0, then I can subtract 10 from both sides. I can divide both sides by negative 16. And listen, I could simplify this, but by taking the square root, this will turn to 4 on bottom. So I'll get root 10 over 4, and this is the time that it takes for this one to hit the ground. So when solving that algebraically, I need to find out for what I can substitute root 10 over 4 into G's equation. And then I want to figure out for what value of K, I need to take my G of T equation. I need to take G of root 10 over 4. And then I need to add some K to it to make it 0. So I need my K value to equal 0 minus G of root 10 over 4. Now I could do this without a calculator, truly, because G of T is negative 8 thirds T squared plus 10. So I can do K equals 0 minus negative 8 thirds times root 10 fourths squared plus 10, which is going to be 0 minus negative 8 thirds times 100, or times, no, that's 10. 10 over 16, it's bringing that back, plus 10. Listen, distributing, I should stop with the 0 minus part of this, right? 0 shouldn't be there. Distributing a negative turns this one positive, turns that one negative. Now, 8/16 is 1/2. 1 times 10 is 10, 3 times 2 is 6, and 10/6 can reduce to 5/3. So this becomes positive 5/3 minus 10, and 10 is 30/3, which gives you negative 25/3. So K should be negative 25/3, which is also negative 8.3 repeating. Okay, so we got to subtract 8.3 repeating from this thing. I'll keep it as negative 25/3 because our G of T equation should now be, this is a transformed one, new G of T is going to be negative 8 thirds T squared plus 10 minus 25/3. Now we just saw what 10, I guess we're going backwards now. 10 minus 25/3 is 30/3 minus 25/3, which brings us back to 5/3. I guess the 5/3 is all I really wanted, right? So G of T equals negative 8 thirds T squared plus 5/3. 5/3 is the height we want to drop this thing from, this many feet. That was the question, right? From what height must the object be dropped on the moon so it hits the ground the same time as Earth? Must be 5/3 feet in the air. That's like 1.6 repeating. It's 1 2/3. So the object must be dropped, I'll say about 1.67 feet from the on the moon. so it hits the ground at the same time as Earth. So that was feasible to do. And I guess this one could have been the same. It's just I dealt with that negative and with the decimal, and I didn't want to do that, whereas this had fractions, so it was fairer. And this only had 2 terms. So this one I did algebraically. What you could do on a graphing calculator for this problem is, and I don't know if I want to do the whole thing because I'd have to reset everything. Whoops, webcam, totally ignore that. That is something to do with Zoom. What I wanted to do here is, you could plug these things in. Maybe I'll do some of it. Plus 10, and this one here would be negative 8/3 x squared. Remember, x is t, and plus 10. Right, these are the originals. Let me kind of reset all this. There's probably a faster way to reset that, but that's okay. Negative 10. Okay, so from here, right, that's one of the graphs. And here's the other graph right there where they drop. You would have to find out what you'd have to find out here. I'm going to zoom in to the origin. You'd have to find out where f, this is f. You'd have to find out where f hits the x-axis, the x value. You'd have to plug in that x value into g, find that height on g, and then subtract 10 from it. All the stuff that I did. But we would say, now the problem is these are all decimals. But what I would do is I would go to calc. I'd find the 0 on, let's see, where, I don't know what my function is. Somewhere between 0 and 1. It's somewhere between 0 and 1. And I'm finding that point of intersection. So this number, this 0.79, etc. I'd have to plug this in. And this was that number that was root 10 over 4. Right? Root 10 over 4 apparently is 0.79, whatever. I'd have to plug this into G's equation. I'd get a y value out, which is the same as the 25/3. And I'd subtract the 25/3 from 10, and I'd get 5/3, which is 1.6, etc. So that's kind of a lot of stuff to do there as well. But yeah, this one at least is exact. Okay, guys, that was a difficult question. I hope not all the others are like that. We'll see. Number 45. How long have we gone? Oh, after more than 2 hours. Number 45. 3 parts. Flying fish use their pectoral fins like airplane wings to guide through the air. Write an equation of the form, vertex form, with vertex 33.5 that models the flight path assuming the fish leaves the water at 0, 0. Okay, so we're going to have something, it leaves the water here, it hits here at 33.5. So we need to make something that hits there and does that. Okay, so, well, this is the h and k. What we need to do is we need to find the a value. Now, there are a lot of ways that I go about this one that might be different from others, but I'm going to follow the textbook format, and then I'll talk about how I'd probably do it afterward. So as far as we're concerned, we have an equation right now that says y equals a times x minus h quantity squared plus k. Our goal is to find out a. Our goal is to find out a. What we can do is use a reference point such as 0, 0. This can be an x, y. And we can find out what that a value is from that. Remember, this is a solution. This is a point that is on the graph. So if I substitute 0 for y and 0 for x, I will find the a value that associates with that. Okay, that's the idea. So negative 33 squared is I don't know what. Let me use the calculator for that one. Clear. Negative, or 33 squared. 33 squared is 1,089. So, and I'm going to subtract 5 over. Negative 5 equals 1,089 times a. So a is negative 5 over 1,089. That is that's the stretch factor. Now, I don't know what 5... Okay, it's not a good decimal. So my equation will be y equals negative 5 over 1,089 times x minus 33 quantity squared plus 5. Weird looking answer, totally. But that's the one for the flying fish to have that stretch factor, to jump from the water then, and then to hit that height, right? That's what we're looking at. Now, what I do would be very equivalent to that. The difference is, I think, if I go over 33, normally I'd go up 33 squared. Oh, excuse me, from here. If I go over 33, normally I would go down 33 squared, but now I'm only going down 5. So I got to figure out, I divide 5 by 33 squared and figure it out. Obviously, I make it negative. I don't use the whole equation bit all the time. That's how I can do stretch factors kind of on my own. That was part A, by the way. Part B. What are the domain and range of the function? What do they represent in this situation? Well, here's the thing on this one. This is where the graph makes more sense for us. Note that the flying fish's model starts when it leaves the water at 0, right there, right? Then it hits a peak height at 5. This is important for range, but then it goes and hits the water again. Now this graph is symmetric. That means if it went 33 feet this way, it also went an additional 33 feet this way at 66, 66,0. The model only applies in the domain from foot number 0 to foot number 66. That's the only time we can track the modeling of the fish's height in flight. And then it goes from 0 feet up to 5 feet. Now you can say, but Mr. Robinson, it came from the water and did this. We don't know what it did in the water differently. It doesn't have gravity in the water. It can have a different kind of speed. It can have different kind of displacement. But from leaving the water to hitting the water again, we can track here. It's not an all real number domain in this case. So part B, let's split this kind of up here. Part B, the domain is going to be from 0 to 66 on X. 0 to 66 and includes both of those. This is in feet. Let me just move this over. This is feet. Range, you know what? I'm going to do this on the next page. I'm going to do this down below. So as long as you understand the graph there, but this is part B. Domain is 0 feet to 66 feet. And the range goes as low as 0 feet in the air up to 5 feet. And it hits the 5 feet. Now it hits the 5 feet at the 33-foot mark, but the fact is there's still more domain to go. So there's that. It says, what do they represent in the situation? The domain represents the horizontal distance the flying fish travels when out of the water. And the vertical distance represents the min and max height, the max height it hits till it goes back down to the water. I mean, to and from, right? It's the distance from the water to its maximum height, basically. I'll say that. Represents the distance from the water to the fish's maximum height. All right. So there's part B. Let's go to part C. Does the value of A change when the flight path has vertex 30, 4? Justify your answer. Maybe. We'd have to play with it. So 30, 4 is our new vertex, and let's play with that. It's still leaving at 0, 0. I mean, I'm going to guess it is. So this A value, by the way, is going to be based off. So here, we did it their way the first time. When I say their way, I mean whatever a teacher would say. Let's do it kind of my way this time now. If you understand anything about the whole 1, 1, 2, 4, 3, 9 stuff. If the vertex is right here, see, think about how we graph this, right? 30, 4. If we graph this, normally we'd go 1, 1, 2, 4, 3, 9, 4, 16. 30, 900, because 900 is 30 squared. But now instead of going 30, 900, we're going 30 over and 4 down. Now we're going down, which means it's negative. That part's fine. But we're going 30 over and 4 down instead of 30 over 900 down. See, we're taking that 900, multiplying it by our stretch factor, and it becomes 4. Well, negative 4. So A is negative 4 over 900, right? Negative 4 over 30 squared. 30 squared. So that's a different number, right? Anyway, that reduces to negative 1 over 225, which is not the same as negative 5 over 1,080, I don't remember the number, 1,089. Is it close? Probably. Let's see. Negative 4 over 900 is negative 0.004 repeating, and negative 5 over 1,089 is negative 0.004591368. They're close. They're not the same. So not the same. A value. Not the same stretch factor, compression factor, whatever you call it. Okay. Oh, you know what else I could have done? Never mind. Nope. All right. Number 46. How do you see it? Describe the graph of g as a transformation of the graph of f of x equals x squared. Well, let's just look at it here. I'm going to mention the translation, although it might have to be a last-ditch resort. We're going to translate 1, 2, 3, 4 to the left, and 1, 2 down. That's our vertex. The stretch seems to be, these are scaled by 1, so 1, 1, 2, 4, 3, 9. There's no change on the stretch or reflections. There's only translation change. So on number 46, describe the graph of g as a transformation. G, we're going to translate f. Let's see, g, let's see. The graph of g is a translation of 4 units left and 2 units down from f. I think that's how we'd say that. All right, that was it. No stretches. Number 47, comparing methods. Let the graph of g be a translation 3 units up and 1 unit right, followed by a vertical stretch by a factor of 2 of the graph of f of x equals x squared. Identify the values of a, h, and k and use the vertex form to write the transformed function. So a is 2, h, 3 and 1 unit right, h is 1, and k is 3. Okay, this one's tricky though, because the stretch factor comes last. Normally it comes first. This says translate 3 units up and 1 unit right, and then followed by this. So g of x, it's going to do the translation. We do 1 unit right, we do 3 units up, but it says followed by a vertical stretch by a factor of 2. That means we stretch not just the that part, we stretch the whole thing. So by a factor of 2 like that. So that means we're going to double that whole thing. So it's 2 times x minus 1 quantity squared, not plus 3, but plus 6. They never said what the vertex was. They said what the translation was. But that is part A. A. Tricky. Oh, this is why they say compare methods. Now try another method. Part B. Use function notation to write the transform function. Compare this with function with your function in part A. Okay, so instead, if I had an interim kind of thing, right, I could say f of x is x squared, and then we'll use an h of x. H of x, we're going to take our f of x and we're going to translate it 1 unit right and 3 units up. So that will now be the x squared. It's x minus 1 squared plus 3. And then they say followed by a vertical stretch. That's where you do them in kind of different order, right? Or you kind of break apart the order. So now we go to g of x. G of x takes h of x and it vertically stretches by a factor of 2. And this is where it shows that you take that thing and you double that whole thing. I can see where that's a lot safer for a question like this in particular. Whoa, should be a square bracket. So g of x officially equals 2 times x minus 1 quantity squared plus 6, like we had before. It's possible. You might have done part A and you would have done it incorrectly, and part B you would have done correctly and said, why are they different? They should be the same. Hopefully you'd recognize they should be. Or go, oh, look, they're different. Okay, well, whatever. No, they should be the same. Part C. Suppose the vertical stretch was performed first, followed by the translations. Repeat parts A and B. Yeah, so this is where, now A is still 2 and all this stuff. So for the first method, this is where I really prefer that first method. It's just straight up. Vertical stretch first is just A goes as it does. F of x, or g of x, equals, did I write g of x the first time? I did. G of x equals vertical stretch of this guy. We translate 1 unit right. We translate 3 units up. Boom, that's the answer just like that, straight up. Okay? 1 unit right, 3 units up, right? Now the second method, you would probably, I mean, it depends on whether you know to be careful or not with this. You could make an h of x in between. Maybe you know that you can do this all in one step. You do the vertical stretch to the function. Within that function, you go 1 unit to the right, and you do translate 3 units up after the stretch. So I think that still works. There's still that next step in between, like that you still have to input this. So that's 2 times the function is x squared. So we're now going to take x, make it x minus 1, and we're going to square it, and plus 3. So they still are the same. Part D, which method do you prefer when writing a transform function? Explain. It really does depend. I mean, it depends on who you are. I'm speaking on my end. It depends on if you can follow the order of operations and what you can do. I would argue on part C, I like that first method more. So in part C, I really like the first method more, knowing that the order of operations take care of themselves when using vertex form. So meaning I can just go straight into vertex form and I'm all good. However, I'm a bit up in the air and would probably, I'll just say, however, I'd probably prefer, and we saw this on an example actually, I'd probably prefer method number 2 for the A-B comparison to avoid any order of operation mistakes. Now, this is especially true when we're not in vertex form. There was an example problem. There was an example problem that was not in vertex form. It was in like factored form or standard form or something like that. It was something different. And I would definitely prefer that method where, especially when you have horizontal things, I would definitely prefer that method of plugging x minus 1 in for x and doing things like that. Otherwise, I would need vertex form to truly know my translations. So yeah, it depends on the thing. I think it depends on which one you're doing. All right. Number 48. 2 more questions. Thought-provoking. A jump on a pogo stick with a conventional spring can be modeled by that. F of x equals negative 0.5. This is vertex form, x minus 6 squared plus 18. Where x is the horizontal distance in inches and f of x is the vertical distance in inches. Write at least one transformation for the function and provide a possible reason for your transformation. Okay. What? This is open-ended. The negative 0.5 is not in reference to gravity. So if I change something, write at least one transforming the function. I don't know what they want me to do. If so, a pogo stick, you know, you're jumping on that thing. This thing is showing you jumping a certain distance over, a certain distance up, things like that. I want to look at what this looks like first of all. I'm assuming this is one of those ones where it's crossing, you know, the origin. So I'm going to graph this. You can take a look at me graphing it here. I'm going to go to the graphing calculator. I want to change negative 0.5 times x minus 6. I'm really just curious to see if it, this is in inches, by the way, crosses the origin. Okay, so something crosses the origin at least. I don't know where it goes back down, but I don't care about that. I just want it to cross the origin. So, okay. I'm not going to change anything in particular. If that's how far off you jump and you do that, great. Only thing I'm going to do is change the height. I'm just going to change the height and say I was jumping down a flight of stairs and one stair was higher than the other. How high up do stairs go? There was actually a math question that said the standard height of stairs is this many inches, like 9 inches. If jumping off a curb, if using a pogo stick to jump off a 9-inch curb and onto street level, the model could instead be, and then I'm going to add 9 to the 18. So I'm going to say g of x equals f of x plus 9. So you add 9 to the 18. G of x is negative 0.5. I don't know if that's what they wanted. I don't know if they wanted me to jump it out further and get a different kind of height and stuff like that. Plus 18 plus 9, or g of x equals. But I want to keep the same model because what I fear is changing the vertex by changing the way I do it or changing the way that this thing springs off or something like that, and then I'm not starting from the origin anymore. So that would really kind of change things. But if I'm jumping off that, now I'm going to kind of land in a different spot, right? So there it is. All right, let's go to the last question on number 49. I mean, that was open-ended, so that was my choice. Number 49, mathematical connections. The area of a circle depends on the radius as shown in the graph. By the way, that's not a circle. What they're saying is as the radius goes up, the area goes up as well, but area increases more than the radius does. A circular earring with a radius of r millimeters has a circular hole with a radius of 3/4 r millimeters. Describe a transformation of the graph below that models the area of the blue portion of the earring. Okay. So area of a circle is pi r squared. However, the earring has a hole with a radius of 3/4 millimeters. What we're doing is we're taking a circle and we're subtracting the other circle out to get this thing. So the area of one minus the area of the other. The area of the earring takes the area of a big circle minus area of hole. Okay? The area of the big circle has a radius of r millimeters. So this is going to be pi r squared minus the area of the hole, which is pi times 3/4 r, quantity squared, like that. It's not just subtracting 1/4 from 3/4 because you got to square them. So pi r squared minus pi times 9/16 r squared. Okay? Or if you factor out pi r squared from this, this is 1 minus 9/16, which is 7/16. So we're taking 7/16 pi r squared. What do they want? Describe a transformation of the graph that models the area of the blue portion of the earring. So we're going from pi r squared to 7/16 pi r squared. So if you imagine that this first one is a sub r equals pi r squared, and I'll call the one earring e sub r equals 7/16 pi r squared. We have to go from this to that. This one is 1, this is 7/16. So what do you have to do? You have to vertically compress a sub r by a factor, stretch factor, or by a factor of 7/16 to make e sub r. That's the transformation that we apply to that. It's just going to be a smaller thing in area compared to the other one that we have. I hope I did that right. That's my idea for it, and I'm sticking to it. That'll be my final answer for that there. And guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching as we finish section 2.5 on this stuff. Coming up next is more on quadratic things. I can't remember. Oh, characteristics, I think, of quadratic functions. I think we're at least going to talk about axis of symmetry. I don't know what else. We'll see. Take care. I'll see you in the next one. I sure hope you've gotten a good form of graphing quadratics, though. All right. Take care. See you in the next one.